You are already here, in the quiet dark, and that is the only place this story needs to begin. There is no need to open your eyes. There is no need to adjust your position or check the time. The room around you is still, and the air is calm, and everything that needs your attention right now is already settled. The story I am going to tell you tonight is a long one, and it moves slowly, like a deep river moving through a wide valley. It will take us from the smallest things we know to some of the largest machines ever built. But we will travel that distance without hurry, one soft step at a time. If you drift off somewhere along the way, that is exactly what this is for. There is no quiz at the end. There is no test of your attention. This voice will keep going, quiet and steady, and you can let it carry you as far as you need to go, or you can let it fade into the background of your rest. Either way is the right way. I want to begin with something very simple, something so basic that you have probably not thought about it since you were a child, in a classroom with warm afternoon light coming through the windows. Everything you can touch, everything you can see, everything you are, is made of tiny pieces. The pillow under your head, the blanket pulled up to your shoulder, the air you are breathing in and out, slow and even. Your own skin, your own bones, the quiet thoughts moving through your mind. All of it, without exception, is built from pieces so small that no eye can see them directly. These pieces are called atoms, and they are the basic building blocks of every material thing in the universe. The word atom comes from an old Greek word that means uncuttable or indivisible, because the people who first thought about these tiny building blocks imagined them as solid little spheres that could not be broken into anything smaller. That turned out not to be quite right, as we will learn later in this story, but the name stuck. Atoms. Tiny, tiny pieces, so small that a single grain of sand contains more atoms than there are grains of sand on an entire beach. So small that the number of atoms in a single glass of water is larger than the number of glasses of water in all the oceans of the world. These are numbers so large they stop meaning anything to a human mind trying to picture them. And that is fine. We do not need to picture the numbers. We just need to sit with the idea that smallness goes much further down than we usually think about. The idea that matter is made of tiny, indivisible pieces is a very old one. It goes back more than 2,000 years, to thinkers in ancient Greece and ancient India who looked at the world around them and wondered what it was made of at the deepest level. They had no microscopes, no laboratories, no way to test their ideas with experiments. They only had their minds, their observations, and their careful thinking. A man named Democritus, who lived in Greece around 2,400 years ago, proposed that if you took a piece of any material and cut it in half, and then cut that half in half, and kept going long enough, you would eventually reach a piece so small that it could not be cut any further. That smallest possible piece, he said, was the atom. At roughly the same time in India, philosophers were developing similar ideas about tiny, indivisible particles that made up the material world. These were not scientific theories in the modern sense. They were deep, patient attempts to think through the nature of reality using only the tools of reason. And the idea they came to, the idea of tiny building blocks, turned out to be astonishingly close to what we now know to be true. Not exactly right, because atoms can be split, as we will see later in this story. But remarkably close, given that these thinkers had nothing to work with but their own curiosity and their own quiet contemplation of the world. For most of human history, that was as far as the idea went. Atoms remained a philosophical concept, something people talked about and debated, but could not see or measure or prove. It was not until the last few hundred years that careful scientists began to gather real evidence that atoms actually existed, and not until the last century or so that we began to understand what they were really like on the inside. This story, the story I am going to tell you tonight, is the slow unfolding of that understanding. It is a walk through decades of patient work by thousands of people, most of whose names we will never know. It is a story about curiosity and caution, about careful measurement and quiet observation. It is also a story about how that deep understanding of tiny things led, eventually, to the building of enormous machines that could light up whole cities. And it is a story about what happened when those machines, built with such care and such hope, sometimes failed. But we are getting far ahead of ourselves. For now, in this quiet beginning, we are just sitting with the idea of atoms, tiny pieces, so small, so fundamental, so easy to forget about in the course of an ordinary day. Think for a moment about your own body, lying here in the dark. Your body is made of cells, and those cells are made of molecules, and those molecules are made of atoms, mostly just a few kinds of atoms. Carbon atoms, the same kind of atoms that make up the graphite in a pencil. Hydrogen atoms, the lightest and simplest kind of atom, the kind that fills the sun. Oxygen atoms, the kind you are breathing in right now. Nitrogen atoms, which make up most of the air around you. A few others, in smaller amounts. Calcium in your bones, iron in your blood, sodium and potassium in the quiet electrical signals moving through your nerves. All of these atoms were made long before the Earth existed, forged inside ancient stars that burned and died and scattered their material across space. The atoms in your body are very old. They have been part of rocks and oceans and air and other living things before they came together to be you, lying here in the dark, listening to these words. That is not a metaphor or a poetic flourish. That is a simple physical fact. The carbon in your skin might once have been part of a leaf on a tree that grew 100 million years ago. The iron in your blood was made in the heart of a star that exploded long before our sun was born. You are, in the most literal sense, made of stardust. And that stardust is made of atoms, the same tiny building blocks that make up everything else. Tonight, we are going to trace the path from that simple recognition that everything is made of atoms to the complex machines we call nuclear power plants. We will start with the early discoveries, the ones that revealed that atoms were not just solid little spheres but had structure inside them. We will learn about the strange glow that certain materials gave off, a glow that could not be explained by any known process, and how that glow led curious people to dig deeper into the heart of the atom. We will follow the careful experiments that revealed the atom's interior, the small dense center called the nucleus, and the particles that make it up. We will learn how those particles could, under certain conditions, be made to split apart, releasing a burst of energy from the very core of matter. And we will follow what happened when human beings, faced with that knowledge, decided to build machines that could harness that energy, first for destruction and then, deliberately and carefully, for peaceful purposes. We will walk through the building of the first nuclear reactors, the first nuclear power plants, the years of growth and optimism, and then the accidents that changed how many people thought about this technology. And we will end, quietly, where we are now, in a present that is still trying to figure out what to do with this powerful and complicated inheritance. But that is the whole long road, and we are not in any rush to travel it. For now, in this first soft section, I just want you to settle into the pace of this story. The pace is slow, the pace is gentle. I will repeat important ideas, not because I think you are not paying attention, but because repetition is comforting, and because when you are drifting near the edge of sleep, hearing something familiar can be like feeling a hand holding yours in the dark. So I will say things more than once, in slightly different words, so that you never have to worry about missing something important. If you feel yourself slipping away, let that happen. The story will still be here, unwinding at its own steady rhythm, and you can pick it up again whenever your attention drifts back, or you can let it go entirely. This is not a lecture. This is a lullaby made of facts, a long, soft thread of history that you can follow as far as you like and then release. Let me tell you a little more about what we mean when we say the word atom. Picture, if you can, a tiny sphere. It is so small that 1,000,000 of them lined up in a row would barely stretch across the thickness of a single human hair. At the center of this tiny sphere is something even smaller, a dense core called the nucleus. The nucleus itself is made of two kinds of particles: protons, which carry a positive electric charge, and neutrons, which carry no charge at all. Around this dense central core, much farther out relative to their size, move even smaller particles called electrons. Electrons carry a negative electric charge, and they move in a kind of cloud or shell around the nucleus. The whole atom is mostly empty space. If you could expand an atom to the size of a large sports stadium, the nucleus would be about the size of a pea sitting at the center of the field, and the electrons would be tiny specks whirling around somewhere in the upper seats. Everything else, all that space in between, is just emptiness. This means that the solid world you feel around you, the firmness of the bed beneath you, the weight of the blanket, the apparent solidity of your own body, is a kind of illusion. What you are actually feeling is the repulsion between the electron clouds of the atoms in your body and the electron clouds of the atoms in whatever you are touching. Nothing ever truly touches anything else at the atomic level. There is always a tiny gap, a space where one cloud of electrons pushes against another cloud of electrons. The sensation of solidity is just the sum of billions of these tiny repulsions happening at once. It is a strange and wonderful thought to fall asleep to. You are not really touching your bed. You are floating on a cushion of invisible forces, held up by the same electric repulsion that keeps atoms from collapsing into each other. The number of protons in an atom's nucleus is what makes it a particular element. 1 proton means hydrogen, the simplest element. 2 protons means helium. 6 protons means carbon. 8 protons means oxygen. 26 protons means iron. 92 protons means uranium, which is an element we will be spending quite a bit of time with later in this story. The number of neutrons, on the other hand, can vary without changing what element the atom is. Atoms of the same element with different numbers of neutrons are called isotopes. This is a word we will return to many times, so let it settle in gently. Isotope. Same element, same number of protons, different number of neutrons. Most elements have several stable isotopes, and some have isotopes that are not stable at all. These unstable isotopes are the ones that eventually fall apart on their own, releasing energy in the process. That release of energy is what we call radioactivity. It is a natural process. It has been happening since the beginning of the universe. Certain atoms are simply too heavy or too unbalanced in their internal arrangement to hold together forever. Eventually they break down, and when they do, they emit particles or energy or both. This is not something human beings invented. It is something human beings discovered, and that discovery is where the next part of our story will take us. But not yet. We are still in the quiet introductory part, the soft opening of a very long tale. I want you to feel, as you lie here, that you are in no hurry. The story will unfold at its own pace, and you can listen to as much or as little of it as your drifting mind allows. Think of it like a long train ride through gentle countryside. The scenery changes slowly. Sometimes you will look out the window and notice the landscape. Sometimes you will close your eyes and just feel the motion. Either way, the train keeps moving, steady and unhurried, and you are safe inside it. That is what this story is. A long train ride through the history of nuclear power, from the first glimmers of atomic theory in the ancient world to the quiet hum of a modern control room. We will pass through moments of great discovery and moments of deep sorrow. We will visit laboratories and reactors and accident sites. We will meet people whose names you might recognize, and many more whose names you will not. And through it all, we will move at this same slow, even pace, never rushing, never raising our voices, just describing what happened and what it means, as calmly and clearly as we can. One more thing before we begin the next leg of our journey. I mentioned earlier that atoms are small, but I did not try to give you a number. Let me try now, not because you need to remember it, but because sitting with a number this large can be its own kind of meditative exercise. A single atom is roughly 1/10,000,000th of a meter across. Written out, that is a decimal point followed by 9 zeros and then a 1. If you took a human hair, which is already very thin, and sliced it lengthwise into 100,000 equally thin strands, each of those strands would still be about 1,000,000 atoms wide. The world of the atom is so far below the scale of our everyday experience that our brains are not really equipped to picture it. And yet, everything we see and touch and are is built from this invisible realm. It is the foundation of all material reality. The screen or speaker you are listening through, the room around you, the city beyond the room, the planet spinning through space, the sun that lights our days, all of it is atoms, arranged in different patterns. The quiet control rooms of nuclear power plants, the massive concrete containment buildings, the fuel rods and the cooling towers and the steam turbines, all of it is atoms. The story we are about to walk through is, at its deepest level, a story about learning to rearrange those atoms in a very particular way, to coax out the energy that holds their dense centers together. It is a story about human cleverness and human fallibility, about hope and caution and the long, slow work of understanding. And it is a story that is still being written even now, even as you lie here in the dark, because we are still figuring out what to do with this knowledge, still debating, still building, still learning. Let that thought settle over you like a second blanket. The story is long, and you are at the very beginning of it. There is no need to stay awake for all of it. The words will keep coming, soft and steady, and you can let them wash over you without needing to hold on to each one. In the next part, we will step back a little further into the history, into the early ideas about atoms and the first real evidence that they existed. We will meet some of the people who did the careful, painstaking work of building the foundations of atomic science. But for now, just rest. Just breathe. Just let the quiet idea of tiny particles, invisible and ancient, hold you in the dark. Everything is atoms. Everything is atoms, and that is enough to know for now. Everything is atoms. That thought settled over you a little while ago, and now we are going to sit with it a bit longer, turning it over slowly, like a smooth stone in the palm of a hand. Because before we can understand the big machines, the power plants and the reactors and the long story of what human beings did with the atom, we need to understand what an atom actually is. We need to build up a small vocabulary, a set of simple words and pictures that will carry us through the rest of this long walk. And the best place to start is with the atom itself, this tiny invisible thing that makes up everything you have ever touched or seen or been. So let us begin again with the atom, but this time let us go inside it. An atom is the smallest piece of a chemical element that still behaves like that element. If you took a piece of pure gold and cut it in half, and cut that half in half, and kept going, you would eventually reach a single atom of gold. That single atom would still be gold. It would have the color of gold, the density of gold, the chemical behavior of gold, all contained in one impossibly small speck. But if you tried to cut that single gold atom in half, you would no longer have gold. You would have something else entirely. Pieces of an atom that are not gold at all. Pieces that could belong to any element. So the atom is the smallest unit that still carries the identity of the thing it makes up. One atom of oxygen is still oxygen. One atom of carbon is still carbon. One atom of uranium is still uranium. That is what makes an atom special. It is the last stop on the way down, where the name of the element still means something. Now, every atom is made of three kinds of smaller pieces. These pieces are called subatomic particles, which just means particles smaller than an atom. The three kinds we need to know about are called protons, neutrons, and electrons. These are the basic building blocks of every atom in the universe. Protons are particles that carry a positive electric charge. Neutrons are particles that carry no electric charge at all, which is why they are called neutrons. The name comes from the word neutral. And electrons are particles that carry a negative electric charge, equal and opposite to the positive charge of the proton. These three particles, arranged in different numbers, give us every element we know. They give us the air in this room, the water in the oceans, the iron in the core of the earth, the hydrogen burning in distant stars. All of it, every material thing, is just different arrangements of protons, neutrons, and electrons. Let us picture an atom now, as best we can. At the very center of the atom is a small, dense core called the nucleus. The nucleus is where the protons and neutrons live, packed tightly together. The nucleus is tiny compared to the whole atom, almost unimaginably tiny. If the atom were the size of a large cathedral, the nucleus would be about the size of a fly buzzing in the very center of that vast space. And yet, almost all the mass, almost all the weight of the atom is packed into that tiny central core. The protons and neutrons are heavy, relatively speaking. The electrons, which move around the nucleus in a kind of cloud or shell, are much, much lighter. In fact, an electron is so light that it would take about 1,800 of them to equal the mass of a single proton or a single neutron. So the heavy part of the atom is the nucleus at the center. The light, airy part is the cloud of electrons that surrounds it, and between the nucleus and the electrons there is nothing. Empty space. Vast stretches of emptiness, relative to the size of the particles. This is what we meant earlier when we said that solid matter is mostly not solid at all. The atom is mostly open space, a tiny heavy center with a whisper of electrons moving far away from it. Now let us look a little more closely at those protons in the nucleus. The number of protons is the most important number for any atom, because the number of protons determines what element the atom is. This is a simple rule and it never changes. One proton in the nucleus means the atom is hydrogen, always hydrogen, no exceptions. 2 protons means helium, 3 means lithium, 4 means beryllium, 5 means boron, 6 means carbon, and so on, all the way up the periodic table, that big chart of elements you might remember seeing on a classroom wall. Each step up adds 1 more proton, and each step takes you to a new element with new properties. Oxygen has 8 protons, iron has 26, gold has 79. Uranium, which we will spend a lot of time with later in this story, has 92 protons. That number, the number of protons, is called the atomic number. It is the atom's fingerprint, its identity card. Change the number of protons and you change the element. There is no other way to do it. So the protons define what the element is. But what about the neutrons? Neutrons sit in the nucleus right alongside the protons, and they play a different role. They do not change the identity of the element. You can add or subtract neutrons from an atom, and it will still be the same element, still have the same chemical behavior, still go by the same name. But adding or subtracting neutrons does change the weight of the atom, because neutrons, as we said, have mass. They are heavy, roughly the same weight as protons. So atoms of the same element can come in different weights, depending on how many neutrons are in the nucleus. These different weight versions of the same element are called isotopes. That is the word I asked you to let settle in earlier, and here it is again, isotope. Let it roll through your mind slowly, like a low wave on a quiet beach. An isotope is simply a version of an element that has a different number of neutrons in its nucleus. Same number of protons, so it is the same element. Different number of neutrons, so it has a different weight. Carbon, for example, always has 6 protons. That is what makes it carbon. But most carbon atoms in the world have 6 neutrons as well, giving them a total of 12 heavy particles in the nucleus. This is called carbon-12. But some carbon atoms have 7 neutrons, for a total of 13 heavy particles. This is carbon-13. And a very small number of carbon atoms have 8 neutrons, for a total of 14 heavy particles. This is carbon-14. All 3 are carbon. All 3 behave chemically as carbon. But they weigh slightly different amounts, and that small difference turns out to matter a great deal. Why does the number of neutrons matter? Because some isotopes are stable, and some are not. A stable isotope is one whose nucleus holds together indefinitely. It does not change. It does not break down. A carbon-12 atom sitting quietly in a piece of charcoal or a diamond or the cells of your body will remain a carbon-12 atom essentially forever. It is stable. It is content with its arrangement of 6 protons and 6 neutrons, but some isotopes have an arrangement that is not quite right. They have too many neutrons, or too few, for the number of protons they carry. This makes the nucleus unstable. An unstable nucleus will, sooner or later, break down. It will rearrange itself into something more stable, and in the process it will release energy. Sometimes it releases a particle. Sometimes it releases a burst of electromagnetic energy, a kind of light that our eyes cannot see. Sometimes it does both. This process of an unstable nucleus breaking down and releasing energy is called radioactivity. It is a natural process, something that has been happening since the beginning of time. It is not something human beings invented. It is something we noticed, something we studied, something we eventually learned to use. But the process itself is as old as the universe. Unstable isotopes are everywhere, in the ground under our feet, in the air we breathe, in the food we eat, in our own bodies. They are a natural part of the world, quietly breaking down, quietly releasing tiny amounts of energy, all the time, without us ever noticing. Let me give you an example that might help this settle in. Uranium, that heavy element with 92 protons, is found naturally in rocks and soil all over the Earth. The most common isotope of uranium in nature is uranium-238, which has 92 protons and 146 neutrons. This isotope is very slightly unstable. It breaks down, but it does so extremely slowly, over billions of years. Another isotope, uranium-235, has the same 92 protons, but only 143 neutrons. This isotope is less stable. It breaks down more readily, and it has another property that turns out to be very important for the whole story of nuclear power. But we will get to that much later. For now, the point is simply this. Atoms of the same element can have different numbers of neutrons, and those different versions are called isotopes. And some isotopes are stable, while others are unstable and radioactive. That is the core idea. Let it rest in your mind, soft and simple. Now let us return to the electrons for a moment, because they matter too. Electrons are the third kind of particle, the light ones with the negative charge, the ones that move around the nucleus in a cloud. Electrons are what make chemistry happen. When atoms bond together to form molecules, which are groups of atoms linked together, they do so by sharing or transferring electrons. The protons and neutrons stay locked in the nucleus, deep and protected. The electrons, being on the outside, are what interact with the electrons of other atoms. This is how water forms. 2 hydrogen atoms sharing electrons with 1 oxygen atom. This is how salt forms. Sodium atoms transferring an electron to chlorine atoms. This is how the long chains of carbon atoms that make up living things are held together. All of chemistry, all of the endless variety of materials in the world, from the softness of cotton to the hardness of diamond, from the transparency of glass to the opacity of steel, comes down to the way electrons arrange themselves around nuclei. The nucleus is the heavy anchor. The electrons are the social, interactive face that the atom shows to the rest of the world. But here is something important to understand. In the story we are telling tonight, the story of nuclear power, we are mostly interested in the nucleus. Chemical reactions, the kind that involve electrons moving around and atoms bonding together, release or absorb relatively small amounts of energy. Burning coal, for example, is a chemical reaction. Carbon atoms in the coal bond with oxygen atoms in the air, releasing heat. That heat can boil water, make steam, and turn a turbine. This is how most of the world's electricity has been made for the last 100 years or so. But the energy released by burning coal comes from the rearranging of electrons. It does not touch the nucleus. The nucleus stays intact, unchanged, holding all its protons and neutrons just as they were before. Nuclear power, by contrast, gets its energy from changes to the nucleus itself. When a nucleus splits, or when two nuclei fuse together, the amount of energy released is vastly larger than anything a chemical reaction can produce. A single uranium nucleus splitting apart releases millions of times more energy than a single carbon atom burning. This is why nuclear power is so concentrated, so potent. A small pellet of uranium fuel, about the size of the tip of your thumb, contains as much usable energy as a ton of coal or several barrels of oil. All that energy is locked up in the nucleus, held there by the forces that bind protons and neutrons together. And the story of how we learn to release that energy, slowly and carefully, in a controlled way, is what we are working our way toward. But we are not there yet. We are still building our vocabulary, still settling these basic ideas into place. Let me go over the main ones once more, very softly, so they can sink in a little deeper. An atom is the smallest piece of an element. It has a nucleus at its center, made of protons and neutrons. Protons have a positive charge, neutrons have no charge. The number of protons determines what element the atom is. Electrons, with a negative charge, move around the nucleus in a cloud. Atoms of the same element with different numbers of neutrons are called isotopes. Some isotopes are stable, meaning they last forever. Some isotopes are unstable, meaning they eventually break down and release energy. That breakdown process is called radioactivity, and the energy locked in the nucleus, the energy that holds all those protons and neutrons together, despite the fact that the protons are all pushing each other apart with their positive charges, is the energy that nuclear power seeks to tap into. That binding force, the thing that overcomes the repulsion of all those positive charges packed into a tiny space, is called the strong nuclear force. It is one of the fundamental forces of the universe, and it is unimaginably powerful over very, very short distances. It holds the nucleus together like a tight fist. And when that fist is opened, when the nucleus is made to split apart, some of that binding energy is released. That is the principle behind everything that follows. Now, none of this was known to the people we met in the last section, the ancient philosophers who first guessed that matter was made of tiny, indivisible pieces. They had no idea about protons or neutrons or electrons. They had no idea about isotopes or radioactivity or the strong nuclear force. All of that understanding came much later, through decades of patient, careful work by thousands of people in laboratories all over the world. And that is where our story is going next. In the next part of this long walk, we will step into the late 19th century, into a world that was just beginning to glimpse the strange inner life of the atom. We will meet a man named Henri Becquerel, who noticed something odd about a piece of uranium salt left on a photographic plate in a drawer. We will meet Marie and Pierre Curie, who followed that oddness into years of painstaking labor, isolating tiny amounts of glowing, energetic material from tons of ore. We will meet Ernest Rutherford, who fired tiny particles at a thin sheet of gold and watched what happened, and in doing so revealed that the atom was mostly empty space with a dense nucleus at its heart. And we will meet James Chadwick, who found the neutron, the last of the three basic particles to be identified, completing our picture of the atom in 1932. This was a journey of decades, from the 1890s to the 1930s, and it had no single moment of breakthrough. It was a slow accumulation of evidence, a gradual sharpening of the picture, a collective effort by many hands and many minds. And in the next part of our story, we will walk through that journey together, at the same slow, steady pace we have been keeping. But for now, you do not need to hold on to any of this too tightly. The words will come back around. Protons, neutrons, electrons, nucleus, isotope, radioactivity. These are the names of the characters in our story, and you will hear them again and again as we move forward. There is no need to memorize them now. There is no need to strain to remember. Just let them drift through your mind, like leaves floating on a slow stream. They will return. The story will circle back and pick them up and carry them along. That is the rhythm we are keeping tonight. Slow, gentle, repetitive enough to soothe, varied enough to hold a half-dreaming attention. If you are still awake, let yourself picture the atom one more time, a tiny, dense sun at the center, made of protons and neutrons huddled together, and far out around it, like planets around a star, the faint cloud of electrons, moving, always moving. And know that this tiny system, this miniature solar system, is repeated trillions upon trillions of times in every object around you, in every cell of your body, in the air you breathe and the bed you rest on. You are made of tiny worlds inside tiny worlds, all of them quietly humming with the forces that hold them together. That is a thought to fall asleep to. That is a thought to carry with you into the dark. You are made of tiny worlds inside tiny worlds, all of them quietly humming with the forces that hold them together. That thought carried you into the dark a little while ago, and now we are going to step forward into the story of how human beings first began to sense that hum, how they first noticed that there was something strange and powerful happening deep inside matter. This part of our story takes place across several decades, roughly from the 1890s to the 1930s, and it involves no single dramatic moment of breakthrough. It was, instead, a slow and careful process, a gradual sharpening of a picture that started out blurry and incomplete. Many hands contributed, many minds worked on different pieces of the puzzle, often without knowing how their piece would fit with the others. And the whole thing began, as so much science does, with someone noticing something odd. The year was 1896. The place was Paris, France. A physicist named Henri Becquerel was studying materials that glowed under light, a phenomenon called phosphorescence. Certain minerals, after being exposed to sunlight, would emit a faint glow for a while afterward, and Becquerel was interested in whether this glow included the newly discovered X-rays that had been making headlines. X-rays had been found by Wilhelm Röntgen in 1895, and they had captured the imagination of scientists everywhere. Becquerel wanted to see if phosphorescent materials gave off X-rays along with their visible glow. His method was simple. He would take a photographic plate, wrap it in thick black paper so no ordinary light could reach it, place a sample of phosphorescent material on top, and set the whole thing in sunlight. If the plate developed dark spots where the material had been, that would mean some kind of penetrating ray had passed through the paper, something like X-rays. He tried this with several materials, and the results were mostly negative, until he tried a compound of uranium, a uranium salt. When he developed the plate after sunlight exposure, he saw darkening. Something had passed through the paper. He assumed, reasonably, that sunlight had been necessary to charge up the uranium salt, to make it phosphoresce. Then the weather in Paris turned cloudy. It was late February, overcast and gray, and Becquerel could not put his experiment out in the sun. He placed a uranium salt sample on a wrapped photographic plate and tucked it away in a dark drawer, waiting for a brighter day. After a few days of waiting, he decided to develop the plate anyway, perhaps just to check that nothing had happened, perhaps out of a kind of restless curiosity. What he found was not nothing. The plate was darkened, just as it had been after sunlight exposure. The uranium salt had fogged the plate without any exposure to light at all. Whatever was causing the darkening was not stored up sunlight. It was something coming from the uranium itself, something constant and internal, something that did not need an outside source of energy to keep going. This was the first clear evidence of what we now call radioactivity. Becquerel had found that uranium emitted a penetrating radiation all on its own, quietly, continuously, without any outside help. He published his findings, and the scientific world took note. But the full meaning of what he had seen would take years more to unfold. The next major steps were taken by a young doctoral student named Marie Sklodowska-Curie, working with her husband Pierre Curie, also in Paris. Marie Curie was looking for a research topic for her doctorate, and she was drawn to Becquerel's uranium rays. She decided to measure them carefully, to see if other materials might also give off this strange radiation. She began testing every element and mineral she could get her hands on, using sensitive instruments built by Pierre and his brother. She found that thorium, another heavy element, also emitted these rays. But the more important finding came when she tested a mineral called pitchblende, a dark, heavy ore from which uranium was extracted. Pitchblende, she found, was much more radioactive than pure uranium itself. This made no sense if uranium was the only source of the radiation. There had to be something else in the pitchblende, something much more strongly radioactive than uranium, present in tiny amounts. Marie Curie proposed the existence of a new element, or elements, still hidden in the ore. What followed was an enormous labor. The Curies obtained tons of pitchblende, which was a waste product from a mine in what is now the Czech Republic. The ore was processed in a large vat, and the Curies worked in a shed with a leaky roof, stirring boiling vats of material with iron rods, for years. Marie Curie described it later as exhausting, difficult work, done through all seasons, in heat and cold. From those tons of pitchblende, they isolated tiny amounts of two new elements. The first they named polonium, after Marie's homeland of Poland. The second they named radium, from the Latin word for ray. Radium was intensely radioactive, millions of times more so than uranium. It glowed faintly in the dark, a pale blue-green light that seemed almost magical. Marie Curie coined the term radioactivity to describe this property, this ability of certain materials to emit rays without any outside stimulation. For this work, the Curies and Becquerel shared the Nobel Prize in Physics in 1903. Marie Curie would later win a second Nobel Prize, this one in chemistry, in 1911, for her continued work on radium and polonium. Now, it is worth pausing here for a moment to note something. The Curies did not fully understand the danger of what they were handling. None of the early researchers did. Radium was so exciting, so novel, that it was incorporated into all kinds of consumer products in the early 20th century. Radium watch dials that glowed in the dark, radium-infused water sold as a health tonic, radium toothpaste, radium cosmetics, radium added to chocolate and bread. The fact that radioactivity could damage living tissue was not yet widely appreciated. Marie Curie herself carried tubes of radium in her pockets, kept it in her desk drawers, and worked with it unprotected for decades. She died in 1934 of aplastic anemia, a bone marrow condition almost certainly caused by her long exposure to radiation. Pierre Curie, who died earlier in a street accident in 1906, had already begun to show signs of radiation sickness. Their laboratory notebooks, even today, are kept in lead-lined boxes, and anyone who wants to study them must sign a waiver acknowledging the radiation risk. The strange glow that had seemed so beautiful and so promising had a cost that took time to become clear. But that cost, that slow understanding of danger, is part of the honest record, and we will sit with it calmly as part of the story. While the Curies were working with radium, other physicists were trying to figure out what radioactivity actually was. The rays given off by radioactive materials turned out to be of several different types. Some were stopped by a sheet of paper. Others could pass through thin metal. By placing radioactive materials in magnetic fields and watching how the rays bent, researchers identified three main kinds of radiation. The first kind, which bent one way in a magnetic field, carried a positive charge and was relatively heavy. These were named alpha particles. The second kind, which bent the other way, carried a negative charge and was much lighter. These were named beta particles. The third kind, which did not bend at all, carried no charge and was the most penetrating of all. These were named gamma rays. We now know that alpha particles are made of 2 protons and 2 neutrons bound together, essentially the nucleus of a helium atom. Beta particles are simply electrons moving at high speed. And gamma rays are a form of electromagnetic radiation, like light but far more energetic, with wavelengths far too short for our eyes to see. This sorting out of the different kinds of radiation was another piece of the slow, patient work of many hands. But understanding what radioactivity was did not yet reveal what the atom looked like on the inside. For that, we need to turn to a different line of inquiry, one that came from a New Zealand-born physicist working in England named Ernest Rutherford. Rutherford had already done important work on radioactivity, classifying alpha and beta radiation, and showing that radioactivity involved the transformation of one element into another, a kind of natural alchemy. But his most famous experiment, the one that really changed our picture of the atom, took place around 1909 to 1911. It is often called the gold foil experiment, and it is one of the quiet milestones in the history of physics. Here is what Rutherford and his colleagues did. They took a source of alpha particles, which as we just noted are relatively heavy, positively charged particles emitted by certain radioactive materials. They aimed a narrow beam of these alpha particles at a very thin sheet of gold foil, so thin that it was only a few hundred atoms thick. Around the foil, they placed a screen coated with a material that would flash with a tiny spark of light whenever an alpha particle struck it. This allowed them to see where the alpha particles went after passing through the gold foil. Most of the alpha particles went straight through the foil, as if it were not there at all. That was not too surprising. If atoms were diffuse, spongy things, as some models at the time suggested, the heavy alpha particles might pass through without much deflection. But a very small number of the alpha particles, something like 1 in every several thousand, bounced almost straight back, as if they had hit something small and very hard. Rutherford later described his reaction with a famous line. He said it was almost as if you had fired a large artillery shell at a piece of tissue paper and it had come back and hit you. The explanation was both simple and profound. The atom could not be a diffuse, spongy ball of material. It had to be mostly empty space, which is why most of the alpha particles passed straight through. But somewhere inside that empty space was something small, dense, and positively charged, something massive enough to stop an alpha particle in its tracks and fling it backward. Rutherford called this small, dense core the nucleus. He calculated that the nucleus was perhaps 10,000 times smaller than the atom as a whole. All the positive charge of the atom and almost all of its mass was concentrated in that tiny central point. The electrons, light and negatively charged, had to be arranged around the nucleus, far away relative to their size, in the vast empty space of the atom. This was the model of the atom that we talked about earlier, the tiny dense sun with a cloud of planets. Rutherford published these findings in 1911, and the basic picture has held up ever since, though it has been refined in ways we will touch on later. Rutherford also identified the proton as a fundamental particle. In experiments around 1919 to 1920, he fired alpha particles into nitrogen gas and observed that hydrogen nuclei were knocked out. He reasoned that the hydrogen nucleus, the simplest possible nucleus with a single positive charge, must be a building block of all other nuclei. He named this particle the proton, from the Greek word for first. So by the early 1920s, the picture was this. Atoms had a small, dense, positively charged nucleus, and that nucleus contained protons. The number of protons determined the element. Electrons orbited at a distance, and their number matched the number of protons in a neutral atom. Radioactivity was the spontaneous emission of particles or energy from unstable nuclei. This was a good picture. It explained a great deal. But it had a puzzle at its center, a puzzle that would take another decade to solve. The puzzle was the neutron. Or rather, the puzzle was the missing piece that the neutron would eventually fill. The nucleus of an atom had a certain mass, which could be measured. It also had a certain number of protons, which determined its electric charge. But the mass and the charge did not match up in any simple way. Helium, for example, had a nucleus with a charge of 2, meaning 2 protons, but its mass was about 4 times the mass of a single proton. If the nucleus were made only of protons, a helium nucleus with 2 protons should have a mass of about 2 proton masses, but it had a mass of about 4. Where was the extra mass coming from? One idea was that there were additional protons in the nucleus, but that they were somehow paired with electrons that cancelled out their charge. This was a workable idea for a while, but it raised theoretical problems. The real answer, when it came, was simpler and more elegant. In 1932, an English physicist named James Chadwick, working at the Cavendish Laboratory in Cambridge, conducted a series of careful experiments that demonstrated the existence of a new particle. This particle had roughly the same mass as a proton, but it carried no electric charge at all. It was neutral, hence the name neutron. Chadwick was building on earlier work by other researchers, including Irene and Frédéric Joliot-Curie in Paris, who had observed a penetrating radiation from certain experiments but had not correctly interpreted what it was. Chadwick designed experiments to test the idea that this radiation was made of neutral particles with mass comparable to a proton. His measurements confirmed it. The neutron was real. For this work, Chadwick was awarded the Nobel Prize in Physics in 1935. With the neutron, the basic picture of the atom was complete. The nucleus contains protons and neutrons. The number of protons gives the element its identity. The number of neutrons can vary, giving rise to isotopes. Electrons orbit the nucleus at a distance. Radioactivity is the spontaneous breakdown of unstable nuclei, often involving the emission of alpha particles, beta particles, or gamma rays. This picture had taken roughly 4 decades to assemble, from Becquerel's fogged photographic plate in 1896 to Chadwick's neutron in 1932. It was not the work of one person or one laboratory or one country. It was a collective, international effort carried out in peacetime, with results published openly and shared freely. Scientists in France, England, Germany, Denmark, Austria, Poland, New Zealand, and many other places all contributed pieces to the puzzle. It was a slow, steady, cooperative building of knowledge, and it forms the foundation for everything that comes next in our story. Now, as you lie here in the dark, I want you to hold that timeline gently in your mind. 1896 to 1932. 4 decades of patient work. No single lightning bolt of revelation. No solitary genius shouting a discovery in a dramatic moment. Just years and years of careful measurement, of thinking and rethinking, of experiments that sometimes worked and sometimes did not, of papers published and read and criticized and improved upon. Becquerel noticing something odd in a drawer, the Curies stirring boiling vats in a leaky shed, Rutherford watching tiny sparks on a screen and realizing that the atom was mostly empty, Chadwick measuring the paths of invisible particles and finding one that had no charge. Each step built on the last. Each discovery opened up new questions, and by 1932, the atom was no longer a vague philosophical idea as it had been for Democritus 2,000 years earlier. It was a mapped territory with a known structure, known components, known rules. Protons, neutrons, electrons, arranged in a nucleus and a cloud. Some nuclei stable, some unstable, some quietly breaking down and emitting energy. All of this was known, and what happened next, as the 1930s unfolded toward the dark horizon of the Second World War, was that people began to wonder what would happen if you deliberately broke a nucleus apart. Not just watched it decay on its own, but struck it hard with a neutron and saw what happened. That wondering is where our next section will take us, into the moment when the atom was split on purpose for the first time, and the enormous energy locked in the nucleus was finally released. But that is for later. For now, just let this part of the story settle around you. The strange glow in the dark, the fogged photographic plate in a drawer, the patient years of work, the slow unveiling of the atom's secret heart. All of it happened. All of it is real, and you, lying here in the quiet, are the inheritor of that knowledge. The atoms in your body, with their dense nuclei and their distant electrons, are the same kinds of atoms that Becquerel and the Curies and Rutherford and Chadwick studied. The forces that hold your atoms together are the same forces they worked so hard to understand. You are part of the same story, the long story of matter and energy and human curiosity. Let that thought be a comfort, a connection to the past, as you drift a little further towards sleep. You are part of a long story, the story of matter and energy and human curiosity, and we left that story at a particular moment. The year was 1932. The neutron had just been found by James Chadwick, and the basic picture of the atom was finally complete. Protons and neutrons in the nucleus, electrons in a cloud around it. Some nuclei stable, some unstable, some quietly releasing energy as they broke down over time. With the neutron now in hand, physicists had a new tool, a new kind of particle to work with. And because the neutron carried no electric charge, it was not repelled by the positively charged nucleus the way a proton would be. A neutron could approach a nucleus without being pushed away. It could drift right up to the surface of the nucleus and, if conditions were right, slip inside. What would happen then was the question that occupied many physicists through the 1930s. One of the people most interested in this question was a man named Enrico Fermi, an Italian physicist working in Rome. Fermi reasoned that neutrons, being neutral, would be especially good at entering nuclei. He began bombarding various elements with neutrons to see what would happen. Starting with the lightest elements and working his way up the periodic table, he and his team observed that many elements would capture a neutron and become a different isotope of the same element, often an unstable one. Sometimes the new isotope would then decay into a different element entirely, through the process of beta decay, where a neutron in the nucleus turns into a proton and emits an electron. Fermi thought that this might be a way to produce new elements, elements heavier than any found in nature. When he got to uranium, the heaviest naturally occurring element, with 92 protons, he expected that capturing a neutron would create an isotope of uranium that would then decay into a new element, something with 93 protons, something never before seen on Earth. He published these results in 1934, and for a few years, it seemed as though he might have succeeded. But the results from the uranium experiments were confusing. The products created by bombarding uranium with neutrons did not behave chemically the way you would expect elements with 93 or 94 protons to behave. They were harder to identify, and their chemical properties did not match the predictions. Other laboratories took up the question. In Berlin, a chemist named Otto Hahn and his younger colleague Fritz Strassmann began working on the problem in the mid-1930s. They were joined at first by Lise Meitner, a physicist from Austria who had worked with Hahn for decades. Meitner was Jewish, and when Germany annexed Austria in 1938, her position became dangerous. With great difficulty, she fled to Sweden in July of that year, leaving Hahn and Strassmann to continue the work in Berlin. The three of them stayed in correspondence, writing letters about the puzzling results, trying to figure out what the uranium experiments were actually producing. The breakthrough came late, in 1938. Hahn and Strassmann performed a careful chemical analysis of the products created when uranium was bombarded with neutrons. They added a small amount of barium, a much lighter element, to the mixture as a kind of chemical tracer, a way to help separate and identify the unknown products. To their deep confusion, they found that they could not separate the barium from one of the radioactive products. Chemically, the unknown product behaved exactly like barium. But barium has 56 protons. Uranium has 92. How could bombarding uranium with a low-energy neutron produce something as light as barium? It made no sense. Hahn and Strassmann checked and rechecked their work. They considered the possibility that the unknown product was radium, a heavier element that has some chemical similarities to barium. They tried again to separate it. They could not. The product was barium. There was no chemical doubt. Hahn wrote to Meitner in Sweden just before Christmas in 1938, describing the result. He called it a frightening conclusion, using a word that conveyed his deep unease with what the experiment seemed to be saying. He knew the chemistry was right, but the physics seemed impossible. Meitner received the letter in the small Swedish town of Kungälv, where she was staying over the Christmas holiday with her nephew, a physicist named Otto Frisch. They discussed the letter on a long walk in the snow. Meitner knew Hahn's chemistry was reliable. If he said the product was barium, it was barium. So they had to explain how a uranium nucleus, struck by a slow neutron, could produce a barium nucleus with about half the mass of uranium. The answer, as they talked it through, walking through the snowy woods, was that the uranium nucleus was not just capturing the neutron and becoming something new. It was breaking apart. The nucleus was splitting into two smaller nuclei, one of which was barium and the other of which would be krypton, an element with 36 protons. 56 plus 36 equals 92. The arithmetic worked. And if the nucleus was splitting, an enormous amount of energy would be released, because the binding energy that held the heavy nucleus together would be partly freed. Meitner calculated the energy release using Albert Einstein's famous equation, relating mass and energy, and the numbers were staggering. A single splitting nucleus would release tens of millions of times more energy than a single chemical reaction, like a carbon atom burning. Otto Frisch returned to his laboratory in Copenhagen and ran an experiment to confirm the idea. He detected the energetic fragments flying away from the split nucleus, and he gave the process a name. He borrowed a term from biology, where binary fission describes the splitting of a cell into two. He called the new nuclear process simply fission, nuclear fission. The splitting of a heavy atomic nucleus into two lighter ones, with a large release of energy. The paper by Meitner and Frisch explaining the theory was published in the journal Nature in February of 1939. The paper by Hahn and Strassmann describing the chemical evidence had been published a month earlier. Together, these two papers announced to the world that the atom could be split, and that splitting it released energy on a scale never before seen in a human-controlled process. Let me pause here and underline something important about this moment. Lise Meitner, who had worked on the uranium problem for years alongside Hahn, who had fled Germany because of persecution, who had provided the physical explanation that made sense of the chemical puzzle, was not included as an author on the Hahn-Strassmann paper. She and Frisch published separately. Meitner was nominated for the Nobel Prize multiple times but never received it. Otto Hahn alone was awarded the 1944 Nobel Prize in Chemistry for the discovery of nuclear fission. The reasons for this are complex, involving the politics of the Nobel Committee, the difficulty of nominating someone from across wartime borders, and perhaps a failure to fully credit Meitner's contribution. The historical record as it stands is clear that her insight was essential. She was the one who, together with Frisch on that snowy walk, first understood what had happened in the Berlin laboratory. Her name deserves to be remembered alongside Hahn's and Strassmann's and Frisch's. The splitting of the atom was the work of all four of them, in different ways, under different and difficult circumstances. Now, the news of fission spread quickly through the international physics community, even as the political situation in Europe grew darker. Physicists everywhere realized that there was something else in the equation, something that made fission not just a laboratory curiosity, but a process that might be harnessed on a large scale. When a uranium nucleus fissions, it does not just produce two lighter nuclei and a burst of energy. It also releases a few free neutrons. Typically, 2 or 3 neutrons fly away from each splitting nucleus, and those neutrons, being neutral, can go on to strike other uranium nuclei, causing them to fission in turn. Those fissions release more neutrons, which cause more fissions, and so on, in a rapidly growing cascade. This is what is called a chain reaction. A single neutron starts the process, and the process multiplies itself. If the conditions are right, the chain reaction can grow extremely quickly, releasing an immense amount of energy in a very short time. If the conditions are controlled differently, the chain reaction can be kept steady, releasing energy at a constant rate. The first kind of chain reaction would lead to a bomb. The second kind would lead to a nuclear reactor and eventually to a power plant. This possibility was not lost on the physicists who first understood fission. Many of them had read the work of a Hungarian-born physicist named Leo Szilard, who had been thinking about chain reactions for years. Szilard had actually conceived of the idea of a nuclear chain reaction as early as 1933, before fission was discovered, and had even patented the concept. Now, with fission confirmed, Szilard saw that the chain reaction was no longer a theoretical idea, it was a practical possibility. And he was deeply worried about who might develop it first. In early 1939, Szilard, along with other physicists including Eugene Wigner and Edward Teller, began to discuss how to alert the United States government to the potential of fission for weapons. They knew that Germany had some of the world's best physicists and that the Nazi regime might pursue a nuclear weapon. They felt an urgent need to act. Szilard decided that the most effective way to get the attention of the American government was through someone whose name carried enormous weight. He approached Albert Einstein, the most famous physicist in the world, who was then living in Princeton, New Jersey. Einstein had not been directly involved in fission research, but he understood the physics immediately. Together, Szilard and Einstein drafted a letter to President Franklin Delano Roosevelt, dated August 2, 1939. The letter explained, in clear and careful language, that recent work in nuclear physics made it possible to conceive of a new kind of bomb, one that would release the energy locked in the atomic nucleus. It warned that Germany might be working on such a weapon, and recommended that the United States government begin its own investigation. The letter was delivered to Roosevelt in October of 1939. It was the beginning of what would eventually become the Manhattan Project, the massive wartime effort to build an atomic bomb. But we are getting ahead of ourselves again. Let me step back from the rush of events and let the core idea of this section settle in more deeply. Fission, the splitting of a heavy nucleus into two lighter ones, releasing energy and free neutrons. This is the fundamental process that makes nuclear power possible. It is not something human beings invented in the sense of creating it from nothing. Fission happens naturally, very rarely, in certain heavy elements. What human beings did was figure out how to make it happen deliberately, in a controlled way, and then how to scale it up. The energy released by fission comes from the nucleus itself, from the strong nuclear force that binds protons and neutrons together. When a heavy nucleus like uranium splits, the two resulting lighter nuclei need less binding energy to hold themselves together than the original heavy nucleus did. The leftover energy is released, mostly as heat. That heat, if produced in large enough quantities, can boil water. The steam can turn a turbine. The turbine can drive a generator. And the generator can produce electricity to light a room, to power a refrigerator, to run a hospital, to keep a city alive through the night. All of that, the whole chain from the splitting of an invisible nucleus to a lit bulb in a quiet house, rests on the insight that came together in those few months at the end of 1938 and the beginning of 1939. The uranium isotope that fissions most readily when struck by slow neutrons is the one we mentioned earlier, uranium-235. It has 92 protons and 143 neutrons, and it makes up less than 1% of natural uranium. Most natural uranium is uranium-238, with 3 more neutrons, and it does not fission easily with slow neutrons. Separating the two isotopes turned out to be an enormous industrial challenge, one that occupied a large part of the Manhattan Project's resources. But the basic principle was clear. If you could get enough uranium-235 together in one place, under the right conditions, you could sustain a chain reaction. You could make a bomb, or you could make a steady source of heat. Let me say all of that again, more simply, because it is the heart of the whole story. An atom of uranium-235 is hit by a neutron. The neutron enters the nucleus. The nucleus becomes unstable and splits into 2 smaller nuclei, typically barium and krypton. The splitting releases a large amount of energy, mostly as heat. It also releases 2 or 3 free neutrons. Those neutrons can hit other uranium-235 nuclei, causing them to split as well. Each of those splits releases more energy and more neutrons. This is a chain reaction. If the chain reaction grows unchecked, it releases its energy in a fraction of a second. That is a bomb. If the chain reaction is carefully controlled, with some neutrons being absorbed before they can cause more fissions, it can be kept at a steady level, releasing heat at a constant rate. That is a nuclear reactor. The heat from the reactor boils water. The steam spins a turbine. The turbine spins a generator. The generator produces electricity. That is a nuclear power plant. This chain of connections, from the neutron to the nucleus, to the chain reaction, to the turbine, to the light bulb, was understood in principle by the spring of 1939. But turning the principle into a working device would take years of immense effort, billions of dollars, and the labor of tens of thousands of people. And the first working device was not a power plant, it was a bomb. The urgency of war shaped everything that followed. The Einstein-Szilard letter set in motion a chain of its own, a chain of decisions and funding and construction that would culminate 6 years later in the deserts of New Mexico and the skies over Japan. That part of the story, the weight of what was built, is something we will face directly in the next sections. But for now, in this quiet moment, I want to leave you with the image of Lise Meitner and Otto Frisch walking through the snow in Sweden, talking through the puzzle that Hahn's letter had posed. A man and his aunt, a physicist and her nephew, walking and talking, working it out. The nucleus splitting, the energy released, the neutrons flying free. No machines, no reactors, no bombs, just two people thinking clearly in the cold air, putting the pieces together. That was the moment when the atom was split in the human mind. Everything that came after, the power and the peril, the lit cities and the exclusion zones, the quiet control rooms and the long debates about waste and safety and the future, all of it traces back to that walk in the snow. A moment of understanding, a quiet turning point in the long story of matter and energy and human curiosity. As you lie here in the dark, let that image drift through your mind. Snow on the ground, two figures walking slowly, their breath visible in the cold air, the pieces of the puzzle clicking into place, one by one, the realization dawning, not with a shout, but with a quiet, steady certainty. The atom can be split, the energy can be released. The world has just changed, and almost no one knows it yet. That is where we will pick up the story next time, with the first deliberate attempt to make a chain reaction happen, in a makeshift laboratory under a sports stadium in Chicago. But that is for later. For now, just rest with the snow and the quiet and the slow turning of understanding. Just breathe, just drift. The atom can be split. The energy can be released. That quiet certainty settled over the world of physics in early 1939, and then the world itself changed. In September of that year, Germany invaded Poland, and the Second World War began in earnest. The scattered community of physicists who had worked together across borders, sharing results openly in journals and at conferences, was now divided by the lines of conflict. The question of whether a nuclear chain reaction could actually be built and controlled stopped being a matter of pure science and became a matter of urgent military interest. The Einstein-Szilard letter had reached President Roosevelt, and the United States government had begun, slowly at first, to organize research into what was now being called the atomic bomb. But before anyone could build a bomb, they had to prove that a chain reaction was possible at all. They had to show that the theory worked in practice. That proof came in a most unlikely place. The place was Chicago, Illinois. The year was 1942. The United States was now fully at war, after the attack on Pearl Harbor in December of 1941. The effort to build an atomic weapon had been consolidated under the code name the Manhattan Project, a vast and secret undertaking that would eventually employ more than 100,000 people across multiple sites. One branch of that work was led by Enrico Fermi, the Italian physicist we met earlier, who had left fascist Italy and come to the United States. Fermi's task was to demonstrate a controlled, self-sustaining nuclear chain reaction, to build, in effect, the first nuclear reactor. The reactor Fermi and his team built was called Chicago Pile-1, often shortened to CP-1. The name was descriptive in a very plain way. It was a pile, a stack, of materials arranged in a particular order. There was nothing sleek or industrial about it. It was not housed in a gleaming laboratory building. The original plan had been to build it in a forest preserve outside Chicago, but a labor strike delayed construction at that site, and Fermi, with characteristic confidence, proposed moving the experiment to the heart of the city. He believed he could control the reaction safely enough to operate it right on the University of Chicago campus. The university administration, perhaps not fully aware of what was being proposed, or perhaps simply trusting Fermi's judgment, agreed. The location chosen was a squash court under the west stands of Stagg Field, the university's football stadium. The court had been unused since the university had suspended intercollegiate athletics for the duration of the war. It was a long, narrow room, about 30 feet wide, 60 feet long, and 26 feet high, with walls of brick and a ceiling that arched gently overhead. Not a cathedral of science, just an old squash court, tucked under the bleachers where students had once cheered for their team. In that room, through the late autumn of 1942, Fermi's team assembled Chicago Pile-1. The pile was a rough sphere, or more accurately, a slightly squashed spheroid, made of alternating layers of graphite and uranium. Graphite is a form of carbon, the same material as pencil lead, but in very pure, dense blocks. It served as what is called a moderator, a material that slows down neutrons. Remember that the neutrons released by fission are moving very fast, and fast neutrons are less likely to be captured by uranium-235 nuclei and cause further fissions. To keep a chain reaction going with natural uranium, which is mostly the non-fissile uranium-238, you need to slow the neutrons down. Graphite does this very well. The neutrons bounce off the carbon atoms in the graphite, losing a little energy with each bounce, until they are moving at just the right speed to be captured by a uranium-235 nucleus and cause another fission. So the design was this: layers of graphite blocks, with lumps of uranium metal and uranium oxide placed at regular intervals throughout. The whole thing was held together by a wooden framework, built by carpenters working from Fermi's sketches. It was, in its way, a handmade device. The most sophisticated nuclear experiment in history, and it was assembled largely by hand, block by block, in a converted squash court. The pile grew over the course of several weeks. As each layer was added, Fermi's team took careful measurements of the neutron activity inside. They knew that at a certain size, the pile would reach what is called criticality. Criticality is the point at which the chain reaction becomes self-sustaining. Each fission produces enough neutrons, on average, to cause exactly one more fission. The reaction does not grow, and it does not die out. It stays steady. Below that point, the pile is subcritical. The reaction fades away. Above that point, the pile is supercritical. The reaction grows. Fermi's goal was to reach exactly criticality, to hold it there for a measured amount of time, and then to shut the pile down safely. It was a delicate operation, a slow approach to a known threshold, like easing a boat up to a dock in still water. To control the reaction, the team used what are called control rods. These were long strips of cadmium metal, a material that strongly absorbs neutrons. When the control rods were inserted into the pile, they soaked up neutrons and kept the chain reaction from getting started. To bring the pile to criticality, the control rods would be withdrawn, slowly and carefully, inch by inch, while instruments measured the neutron count. Fermi had calculated exactly how far the rods needed to be pulled out to reach the critical point. He had also designed safety systems. One control rod was operated by a simple electric motor. Another was held in place by a rope that could be cut with an axe if something went wrong. A third was a zip rod, a rod that could be pulled out quickly and dropped back in just as fast. And there was a safety rod held by an electromagnet. If the power failed, the magnet would release and the rod would drop into the pile under gravity. And then there was the liquid control squad, a team of 3 young physicists who stood on a platform above the pile with buckets of a cadmium salt solution. If all the mechanical controls failed, they were to pour the solution over the pile to absorb neutrons and stop the reaction. It was a low-tech backup to a high-stakes experiment, a reminder of just how improvised this whole enterprise was. December 2nd, 1942, was a cold day in Chicago. The temperature outside was well below freezing. About 40 people gathered in the squash court that morning to witness the experiment. They included Fermi's team, some other Manhattan Project scientists, and a few officials. They stood on a balcony that had been built along one wall of the court, looking down at the dark gray mass of the pile. Fermi was in charge, calm and methodical as always. He had a small slide rule in his hand, a simple analog calculating device, and he used it to check his predictions as the experiment proceeded. The morning was spent gradually withdrawing the main control rod, step by step. At each step, Fermi checked the neutron count on the instruments and compared it to his calculations. The numbers matched his predictions closely. The pile was behaving exactly as theory said it should. Around mid-morning, Fermi ordered the main control rod pulled out to the point where his calculations said criticality would be reached. But the neutron count rose and then leveled off, just below the critical mark. Fermi checked his slide rule. He had expected this. The pile was not quite large enough yet, or rather, the control rods were not quite far enough out. Some neutrons were still being absorbed by the cadmium. He ordered the rod withdrawn a little further, and then he paused the experiment for lunch. He wanted everyone to eat and rest before the final push. It is a detail worth dwelling on. The man orchestrating the first controlled nuclear chain reaction in history broke for lunch. He ate, presumably something simple, and then he and his team returned to the squash court in the early afternoon. The experiment resumed at around 2 o'clock. Fermi ordered more of the control rod withdrawn. The neutron count began to climb again, and this time it did not level off. It kept rising, slowly but steadily, the instruments clicking faster and faster, the pens on the chart recorders tracing a line that curved upward and kept curving. Fermi watched the instruments, his slide rule in hand, his expression unchanged. He checked the numbers. The pile had reached criticality. The chain reaction was self-sustaining. Neutrons were causing fissions, and those fissions were producing more neutrons, and those neutrons were causing more fissions, in a steady, unbroken chain. For the first time in human history, a controlled nuclear chain reaction was taking place. The pile operated for about 28 minutes. The power level was very low, just a fraction of a watt, barely enough to light a small bulb. There was no visible sign that anything momentous was happening. No glow, no hum, no vibration. Just a pile of graphite and uranium sitting in a squash court, with instruments softly clicking. A few of the scientists present later described a sense of quiet awe, a feeling of being present at a hinge point in history. But the moment itself was remarkably undramatic. Fermi, after letting the reaction run for a while, ordered the control rod reinserted. The neutron count dropped. The chain reaction stopped. The pile was subcritical again. The experiment was over. One of the scientists present, a physicist named Arthur Compton, placed a coded phone call to James Conant, the chairman of the National Defense Research Committee, to report the success. Compton said, "The Italian navigator has landed in the New World." Conant asked, "How were the natives?" Compton replied, "Very friendly." It was a prearranged code, a bit of theater to mark a moment that could not yet be spoken of openly. The world outside the squash court knew nothing of what had just happened. The war ground on. The work of the Manhattan Project continued in secret. But the fundamental question had been answered. A controlled nuclear chain reaction was possible. The atom had been not just split, but harnessed, held in a steady state by human design. Let me sit with that moment a little longer, because it deserves a slow and careful telling. Picture the scene. A cold December day in a Midwestern American city, a converted squash court under a football stadium, a pile of dark gray blocks, nearly 400 tons of graphite, embedded with lumps of uranium, a wooden framework, carpentered by hand, a balcony with a few dozen people in wool suits and ties, watching dials and chart recorders. A man with a slide rule, calm and steady, giving quiet instructions, and then the line on the chart paper begins to curve upward, and it keeps curving, and everyone in the room understands that something new is happening, something that has never happened before on the surface of the Earth. A chain reaction, sustained and controlled, the same process that had been splitting atoms quietly in the rocks for billions of years, the same process that Lise Meitner and Otto Frisch had explained on their walk in the snow, was now running under human direction. It was a moment of deep technical achievement. It was also a moment whose consequences were far from clear. The same knowledge that had made the pile possible would, in less than 3 years, be used to build weapons of a kind the world had never seen. That is the weight of what was built, and we will turn to face it directly in the next part of our story. But for this moment, in this section, I want to hold on to the quiet of the squash court, the absence of drama, the calm, methodical way Fermi approached the threshold and crossed it, and then crossed back again, shutting the pile down before the end of the working day. There is a photograph, taken later, of Chicago Pile-1. It shows a rough, dark mound of blocks, unremarkable, almost ugly. It looks more like a pile of coal in a basement than one of the most significant experiments of the 20th century. That is part of what makes the story so striking. The first nuclear reactor was not a gleaming machine in a high-tech laboratory. It was a handmade stack of bricks in a room that smelled of old sweat and floor polish. It was built in a hurry, under wartime secrecy, with materials that were scarce and difficult to purify. The graphite had to be extraordinarily pure. Even tiny amounts of certain impurities would absorb too many neutrons and kill the reaction. The uranium had to be cast into precise shapes. All of this was done by a team working under immense pressure, knowing that if they succeeded, a bomb would almost certainly follow, and if they failed, the war might end differently. And yet, in the moment of the test itself, there was no rush. Fermi took his time. He broke for lunch. He checked his numbers carefully. He advanced the control rod inch by inch, watching the instruments, never hurrying, never hesitating. It was a demonstration of a particular kind of scientific temperament, the ability to remain calm and precise, even when the stakes are as high as they can be. Let me describe the pile itself a little more, because the physical details are part of the texture of this history. The graphite blocks were cut into precise rectangles, about 4 inches by 4 inches by 16 inches, and they were stacked in layers. Some of the blocks had holes drilled into them to hold the uranium. The uranium came in 2 forms. Some was pure uranium metal, pressed into small cylinders, and some was uranium oxide, a dark powder pressed into pellets. The metal was produced by a company in Iowa, using a process that was itself new and difficult. The graphite came from a manufacturer that had to develop special purification methods. Everything about the project pushed the limits of what American industry could do at the time. And yet the final assembly was done by hand, by a crew that included high school dropouts and former construction workers alongside PhD physicists. Fermi's team was a mix of people, some of them refugees from Europe, some of them young American scientists just starting their careers. They worked in shifts, in the cold and the dust, laying block after block, checking and rechecking, building the pile, layer by layer. It was an industrial process conducted at a craft scale, a bridge between the old world of laboratory physics and the new world of giant engineering projects. The squash court itself, if you could have stood in it before the pile was built, would have seemed an ordinary, slightly shabby room. It had been used for squash, a game played with rackets and a small rubber ball, and then it had been abandoned when the war started and the university's priorities shifted. The walls were cream-colored brick, scuffed and marked from years of use. The floor was wooden, polished in the center from the movement of players' feet. The ceiling arched up to a row of windows near the top, but those windows were painted over for secrecy. No one outside was to know what was happening in there. The only light came from bare bulbs hanging from cords. In the winter cold, the room was drafty and difficult to heat. The scientists worked in coats and hats. It was, by any measure, an unlikely birthplace for the atomic age. But that is often how history works. The important things happen in quiet, out-of-the-way places, witnessed by small groups of people who know they are doing something significant, but cannot yet know the full shape of what it will become. After the successful test on December 2nd, the pile was run again on several subsequent occasions, mostly to test measurements and train operators. Then, early in 1943, it was dismantled and moved to a new site outside Chicago, a place called Argonne, where a larger and more permanent reactor was built. The squash court was eventually cleaned up and used for other purposes. The university later placed a plaque on the building, and the site is now a National Historic Landmark. But at the time, the whole thing was done quietly, with no public announcement, no press conference, no celebration. The war was on, and the real work was just beginning. The knowledge gained from Chicago Pile-1 fed directly into the design of the large reactors that would be built at Hanford, Washington, to produce plutonium for the atomic bomb. The chain reaction that Fermi had demonstrated on a tiny scale would soon be scaled up to industrial proportions, producing heat and radiation on a level that the little pile under the stadium could only hint at. We are now at a turning point in our long, slow walk through this history. Behind us are the decades of patient discovery, the fogged photographic plates, the snowy walk in Sweden, the splitting of the atom. Ahead of us are the bombs, and then the power plants, and then the accidents, and then the present day with all its debates and uncertainties. But right here, in this moment, we are in the squash court, on December 2nd, 1942, watching the chart recorder pens trace their upward curve. The Italian navigator has landed, the chain reaction is running, the world has changed, and no one outside this room knows it. Let that image settle over you like the quiet of a cold afternoon, the hush of a room full of people watching something new come into being. There is no explosion, there is no drama, there is just a pile of dark blocks, and a man with a slide rule, and the soft clicking of instruments counting things too small to see. That is the true beginning of nuclear technology. Everything that follows, the power and the peril, the lights and the shadows, starts here, in this quiet room under a stadium, in the middle of a war, in the middle of a city, in the middle of an ordinary winter day. As you drift now, let the quiet of that room become your quiet. Let the slow, steady clicking of the neutron counters become a kind of lullaby. The pile is still there, in the past, humming softly to itself, splitting atoms one by one by one. It is not a weapon, it is not a power plant. It is simply a proof, a demonstration that the universe allows this, that the laws of physics permit us to hold a piece of the sun in our hands, if we are careful enough, if we are steady enough, if we take our time. And Fermi did take his time. He broke for lunch. He checked his slide rule. He advanced the rod inch by inch. There is a lesson in that, a kind of wisdom that the rest of this story will test again and again. The forces we are dealing with are vast. The only way to handle them is with patience, with care, with a kind of quiet attention that does not rush and does not panic. That is how it began, in a squash court in Chicago, and that is how we will leave it for now, as we prepare to turn toward the harder chapters ahead. The chain reaction ran for 28 minutes. Then it stopped. The room was quiet again. The war went on, but nothing would ever be quite the same. The chain reaction ran for 28 minutes, and then the room was quiet again. The war went on. Nothing would ever be quite the same. We left our story in December of 1942, with the controlled chain reaction achieved under a football stadium in Chicago. That experiment was not an end in itself. It was a stepping stone, a proof that the physics worked, and the work that followed it was aimed at a single, urgent goal: building a working atomic weapon before Germany could. The Manhattan Project, which had been organizing itself since the Einstein-Szilard letter of 1939, now accelerated into the largest scientific and industrial undertaking the world had ever seen. And because this is history, not a story that can skip over the hard parts, we need to sit with what that project produced. We need to do it calmly and honestly, without drama, without dwelling on graphic detail, but also without looking away. The Manhattan Project was a vast network of facilities spread across the United States. At Oak Ridge, Tennessee, enormous plants were built to separate uranium-235 from the more common uranium-238, using several different methods, all of them difficult and expensive. At Hanford, Washington, large reactors were constructed to produce a new element, plutonium-239, which could also serve as fuel for a bomb. At Los Alamos, New Mexico, a remote laboratory was established on a mesa in the desert, where physicists and engineers designed the weapons themselves, working under the scientific direction of J. Robert Oppenheimer. The whole project employed more than 100,000 people, yet it was kept so secret that most of those workers had no idea what they were building. They knew only their own small piece of the puzzle. The full picture was held by a very small number of people at the top. The work culminated in the summer of 1945. By then, Germany had surrendered. The war in Europe was over. The war in the Pacific against Japan continued with fierce fighting. On July 16, 1945, the first atomic bomb was tested in the desert of New Mexico at a site called Trinity. It was a plutonium implosion device, the same design as the bomb that would later be dropped on Nagasaki. The test confirmed that the weapon worked, releasing an amount of energy equivalent to about 20,000 tons of TNT. The flash was seen from hundreds of miles away. The mushroom cloud rose more than 7 miles into the sky. The desert sand beneath the blast was fused into a glassy mineral that was later named trinitite. The atomic age had moved from theory to demonstration. Less than a month later, on August 6, 1945, a uranium gun-type bomb called Little Boy was dropped on the city of Hiroshima, Japan. It detonated about 1,900 feet above the city. On August 9th, a plutonium implosion bomb called Fat Man was dropped on Nagasaki. These two bombings, together with the Soviet Union's declaration of war on Japan, led to Japan's surrender on August 15, 1945. The Second World War was over. The number of people who died in the two cities is not known with precision. Estimates vary, but the most commonly cited figures are that roughly 100,000 to 200,000 people, most of them civilians, died as a result of the two bombings, either immediately or in the months that followed from injuries and radiation sickness. These are large, imprecise numbers, and the difficulty of counting the dead in the chaos of a destroyed city means that any exact figure is an estimate. What can be stated plainly is that the bombs caused immense human suffering and that their use marked a profound change in the nature of warfare. For the first time, a single device could destroy a city in a moment. The world understood immediately that something fundamental had shifted. I am not going to describe the effects of the bombs in detail. That is not what this story is for. But I am also not going to pretend that this part of the history did not happen. The same physics that would later light cities, that would run turbines and generate electricity for millions of homes, was first used to build weapons. The connection is direct and inescapable. The Manhattan Project was a weapons program. Chicago Pile-1 was built to gather data for bomb design. The reactors at Hanford were built to produce bomb fuel. The first purpose of nuclear fission in human hands was destruction. That is a fact of the historical record, and we will sit with it calmly, without turning away. In the years immediately after the war, the United States had a monopoly on atomic weapons. That monopoly ended in 1949, when the Soviet Union tested its own atomic bomb. The Cold War between the two superpowers was now a nuclear arms race. Both nations built larger and more powerful weapons, moving from atomic bombs, which use fission alone, to hydrogen bombs, which use fission to trigger fusion and can release energy on a scale thousands of times greater than the Hiroshima bomb. The world learned to live under the shadow of these weapons. The possibility of annihilation, of a war that no one could win, became a constant background fact of international politics. That shadow has never fully lifted. It is with us still. But our story tonight is not primarily about weapons. It is about the other use of nuclear fission, the peaceful use, the effort to take the same chain reaction that Fermi had demonstrated and turn it into a source of electricity. And that turn, that deliberate pivot from weapons to power, has its own history. It did not happen automatically. It had to be chosen, argued for, and built. The key figure in that turn was a man named Dwight David Eisenhower, the 34th President of the United States, who had been the supreme Allied commander in Europe during the war. Eisenhower had seen the destruction of war firsthand. He understood, perhaps better than most, what nuclear weapons meant, and in his first term as president, he decided to make a public case for a different path. On December 8, 1953, Eisenhower addressed the United Nations General Assembly in New York. The speech he gave is remembered as the Atoms for Peace speech. It was a carefully crafted address, broadcast on radio and television, aimed at a global audience. Eisenhower spoke frankly about the destructive power of nuclear weapons, which he called a dread secret. He acknowledged that the United States and the Soviet Union were locked in a dangerous arms race. But he also proposed something else. He proposed that the nations of the world should pool their nuclear knowledge, contributing fissile material from their weapons stockpiles to an international agency that would use it for peaceful purposes. He spoke of providing abundant electrical energy in the power-starved areas of the world. He spoke of applying nuclear technology to medicine and agriculture. He framed the atom not as a curse, but as a tool that could be turned toward human benefit, if only the nations of the world could find the wisdom to cooperate. The speech was a political act, of course. It was designed in part to shape public opinion, to position the United States as a peaceful nation, even as it continued to build its nuclear arsenal. But it was also a genuine opening. Eisenhower's words set in motion a series of concrete actions. In 1957, the International Atomic Energy Agency, often referred to as the IAEA, was founded with headquarters in Vienna, Austria. Its mission, as stated in its charter, was to accelerate and enlarge the contribution of atomic energy to peace, health, and prosperity throughout the world. The IAEA was given the task of promoting nuclear safety, facilitating the sharing of nuclear technology for civilian use, and monitoring nuclear materials to ensure they were not diverted to weapons. It was an imperfect institution, limited by the politics of the Cold War and the interests of its member states, but it was a real one. It still exists today. It still does that work. The Atoms for Peace speech marked a shift in public mood. Before 1953, nuclear energy was almost exclusively associated with weapons, with secrecy, with military power. After 1953, the idea that the atom could light homes and power factories began to take hold in the public imagination. It was a reassuring thought, a hopeful one. The same force that had destroyed cities could be tamed, controlled, put to useful work. It was an appealing narrative, and it helped to justify the enormous expense of nuclear research. Governments around the world, not just in the United States and the Soviet Union, but also in the United Kingdom, France, Canada, and elsewhere, began to invest in nuclear power programs. The first generation of nuclear power plants was being designed and built, even as Eisenhower spoke. But let me slow down here and make sure we are holding both sides of this story at once, because that is the honest way to tell it. The turn from weapons to power was real. The Atoms for Peace program led to the sharing of nuclear technology with countries around the world. It also, in some cases, provided cover for nations to develop the technical expertise that could later be used to build weapons. The same reactors that produce electricity can also produce plutonium. The same enrichment technology that makes fuel for power plants can also make fuel for bombs. The line between civilian and military nuclear technology is thin, and it has always been thin. This is not a secret or a scandal. It is a simple technical fact. The International Atomic Energy Agency was created in part to manage that tension, to monitor and verify that civilian programs stayed civilian. The tension has never been fully resolved. It is built into the nature of the technology itself. As you lie here in the dark, I want you to feel the complexity of this moment in the story without being disturbed by it. This is not a simple tale of progress, of science marching forward from discovery to discovery toward a brighter world. It is a human story, full of human choices, some of them wise, some of them short-sighted, some of them made under pressures that are hard to imagine from a distance. The people who built the bombs were not cartoon villains. Many of them were physicists who had fled fascism, who believed they were in a race against a German bomb, who felt that the war had to be ended as quickly as possible. The people who built the first power plants were not naive dreamers. They were engineers who understood the risks and believed they could manage them. The politicians who funded both were balancing national security, economic interests, and public opinion. All of these people were working with a technology that was less than a decade old, a technology whose long-term consequences were still largely unknown. They made their choices with the information they had, in the circumstances they were in. That is all any generation can do. Now the mood is shifting again, in our story, from the weight of the bomb toward the possibility of power. In the next section, we will walk into the first nuclear power plants, the ones that actually generated electricity and sent it out into the grid. We will visit Obninsk in the Soviet Union, Calder Hall in the United Kingdom, and Shippingport in the United States. We will see how the chain reaction that Fermi had controlled in a squash court was scaled up, contained, and connected to steam turbines. We will watch the first lights come on, but before we go there, let us stay a moment longer with Eisenhower's speech, with that moment of deliberate turning. It was December of 1953. The United Nations building in New York, a sleek glass tower by the East River, was still quite new. The delegates sat in a large auditorium, wearing the formal dress of the era, the men in dark suits, the women in hats and gloves. Eisenhower stood at the podium, his glasses reflecting the television lights, and he spoke of swords and plowshares, an old biblical image of turning weapons into farming tools. He did not pretend that the danger was past. He did not minimize what had been built, but he pointed to a different future, one in which the atom was not a threat, but a gift, not a shadow, but a light. It was a speech that changed how many people thought about nuclear energy. It opened a door. And through that door, in the years that followed, walked the engineers and the builders, the welders and the pipe fitters, the technicians and the operators, all the people who would take the next steps in this long story. The first power plants were already on the drawing boards. Some were already under construction. The quiet engine was about to leave the laboratory and enter the world. That is where we will go next, into the first halls of nuclear power, where steam first spun a turbine with heat from split atoms. But for now, just rest with the turning. The long arc of this story, from a fogged photographic plate to a lit home, bends here, in this pivot from war to peace. It is not a clean break, it is not a simple story, but it is our story, the story of what we did with the knowledge we gained. And you, lying here in the quiet, are part of that arc, part of the world that inherited both the weapons and the power, the dread and the hope, the shadows and the light. Let that settle. Let it rest. Breathe slowly, and let the next part of the journey come when it comes. Eisenhower's words opened a door, and through that door, in the years that followed, walked the engineers and the builders. The quiet engine was about to leave the laboratory and enter the world. And the first place it did so, the first place where a nuclear reactor sent electricity out into a public grid and lit actual homes, was not in the United States, and not in the United Kingdom, but in the Soviet Union. The town of Obninsk sits about 60 miles southwest of Moscow, along the banks of the Protva River. In the early 1950s, it was a small, unremarkable settlement, the kind of place that might not appear on a map unless someone had a reason to put it there. The Soviet government had a reason. They built a physics and engineering institute there, dedicated to nuclear research, and on the grounds of that institute, they constructed a small power plant. It was called the Obninsk Nuclear Power Plant, and it was the first nuclear plant in the world to produce electricity for a public grid. On June 27, 1954, the plant was connected to the electrical network, and the power it generated began flowing to nearby homes and businesses. The output was modest by later standards, about 5,000 kilowatts of electrical power, which would be written out as 5,000 kilowatts. That is enough to supply a few thousand homes, a small town, nothing on the scale of what would come later, but it was a proof. It was a demonstration that the chain reaction could be sustained not for 28 minutes under a football stadium, but for days and weeks and months, boiling water, making steam, spinning a turbine, and producing electricity that people could use to light their rooms and run their appliances. The Obninsk plant used a reactor design that was different from the simple graphite pile Fermi had built. It was what is called a channel-type reactor, where the fuel is placed in individual channels through which water flows to carry away the heat. The moderator, the material that slowed the neutrons down, was graphite, the same material Fermi had used. The fuel was uranium enriched to about 5% uranium-235, a higher concentration than natural uranium, but lower than weapons-grade material. The plant operated for many years, continuing to produce both electricity and heat for the local area until it was finally shut down in 2002. By then, it had been running for nearly half a century. It is still there today, a museum piece now, a monument to the beginning of civilian nuclear power. You can visit it, walk through the control room, see the dials and switches that the operators used. It is a quiet place now, silent except for the footsteps of visitors. But for 48 years, it hummed with the steady flow of steam and electricity. Now, if Obninsk was the first to light up, the United Kingdom was not far behind. On the coast of Cumbria, in the northwest of England, near the Irish Sea, there is a site called Calder Hall. It was built at a place named Sellafield, which had been a site for nuclear weapons production since the late 1940s. Calder Hall was different. It was designed from the start to produce electricity for the public grid, and it is generally considered the first commercial-scale nuclear power station in the world. The plant had 4 reactors, and the first of these began operating in 1956. On October 17th of that year, Queen Elizabeth II visited Calder Hall and formally opened it, pulling a lever that connected the plant to the national grid. The event was covered widely in the press, and the photographs from that day show the Queen in a pale coat and hat, standing in a control room, surrounded by engineers in suits and ties. It was a carefully staged moment, intended to signal that the United Kingdom was at the forefront of peaceful nuclear technology. The fact that Calder Hall was built next to a weapons production site and that its reactors could produce both electricity and plutonium for military use was not emphasized in the public announcements. But that dual purpose was part of the reality of early nuclear power. The line between civilian and military was, as we have noted before, often thin. Calder Hall's reactors were of a type called magnox, named after the magnesium-aluminum alloy used to clad the uranium fuel rods. They were gas-cooled reactors, meaning that the heat from the reactor core was carried away by carbon dioxide gas rather than by water. The hot gas was then used to boil water into steam, which spun the turbines. The plant produced about 200,000 kilowatts of electrical power when all 4 reactors were running, enough to supply a medium-sized city. Calder Hall operated for 47 years, finally shutting down in 2003. By then, it had been far surpassed in size and efficiency by newer plants, but its place in history is secure. It was the first nuclear power station to feed a substantial amount of electricity into a national grid on a commercial basis. The lights that came on in British homes starting in 1956 were, in part, lit by the splitting of atoms. And then came the United States. The Shippingport Atomic Power Station, located on the Ohio River, about 30 miles northwest of Pittsburgh, Pennsylvania, was the first full-scale nuclear power plant in the United States designed exclusively for civilian use. It was a project of the Atomic Energy Commission, the American government agency that oversaw nuclear development, and it was built in collaboration with the Duquesne Light Company, a local electric utility. The plant was situated on a site that had originally been intended for a much larger power plant, but the project was scaled down to serve as a demonstration. The reactor was a pressurized water reactor, a design that would become the most common type in the world in the decades that followed. In this design, water is kept under high pressure so that it does not boil, even when heated to very high temperatures. This hot, pressurized water is then circulated through a heat exchanger, where it transfers its heat to a separate loop of water, which does boil into steam. The steam then drives a turbine. The advantage of this design is that the radioactive water in the reactor core stays in its own sealed loop and does not come into contact with the turbine or the outside environment. Shippingport began operation on December 18, 1957, and it was connected to the grid shortly thereafter. The ceremony was attended by officials from the government and the utility, and it was hailed as a milestone in the peaceful use of atomic energy. The plant produced about 60,000 kilowatts of electrical power, and it operated until 1982. When it was finally shut down and dismantled, the site was cleaned up and released for unrestricted use, a demonstration that nuclear decommissioning could be done thoroughly and safely. Shippingport was small by modern standards, but it established the basic template that many later plants would follow: a pressurized water reactor, a sealed primary coolant loop, a steam generator, and a turbine hall where the electricity was actually produced. If you have ever seen a picture of a nuclear power plant with its large, dome-shaped containment building, you are looking at a descendant of the design principles first proven at Shippingport. Let me slow down here and gather these 3 plants together, because they represent something important. Obninsk in 1954, Calder Hall in 1956, Shippingport in 1957, 3 different countries, 3 different reactor designs, 3 different approaches to the same fundamental challenge: taking the heat from splitting atoms and using it to make electricity. The fact that these 3 plants came online within a few years of each other is not a coincidence. It reflects the intense interest that governments around the world had in nuclear power in the 1950s. The technology was new, but the promise was enormous. A single load of uranium fuel could produce as much energy as trainloads of coal or shiploads of oil. A nuclear plant did not need to be constantly fed with fossil fuels delivered by rail or pipeline. It produced no smoke, no soot, no ash. In an era when cities were choking on coal smoke and industrial pollution was a visible daily reality, nuclear power seemed clean, modern, even futuristic. The fact that it also carried risks that would become painfully clear in the decades that followed, was not yet widely appreciated. The mood in the 1950s was one of optimism, of a belief that technology could solve old problems and create a better world. The first nuclear power plants were built in that spirit. Let me describe what it might have been like to stand in one of these early control rooms. Picture a long room with walls lined with instrument panels, gray-green metal cabinets filled with dials and switches and chart recorders. The lighting is soft, indirect, coming from fixtures mounted above the panels. The operators sit at consoles, watching needles move on gauges, checking levels and temperatures and pressures. There is a low, steady hum in the room, the sound of electronics and ventilation systems. On the wall, a large board shows the status of the reactor, control rod positions, coolant flow rates, temperature readings at various points in the core. Everything is calm, orderly, methodical. The reactor itself is not visible. It is sealed inside a thick concrete containment building, submerged in water, or surrounded by shielding. The only sign of its operation is the movement of the needles on the dials, the steady flow of numbers on the chart paper. It is a quiet kind of work, monitoring a process that is vast and powerful, but entirely invisible. The operators cannot see the chain reaction. They cannot see the neutrons flying, the atoms splitting, the heat building. They see only the instruments that measure these things, and they trust those instruments, and they trust the design of the plant that contains and controls the reaction. In the early days, that trust was high. The plants had been designed by the same people who had built the first reactors, the pioneers of the Manhattan Project and their students. The operators were highly trained, often recruited from the nuclear navy or from graduate programs in physics and engineering. The culture was one of rigor and caution, at least in principle. Now, it is worth noting that these first plants were not purely civilian in their origins or their purposes. Obninsk was built by the Soviet nuclear establishment, which was deeply intertwined with the weapons program. Calder Hall, as I mentioned, produced both electricity and weapons-grade plutonium. Shippingport, while designed for civilian power, was built by the Atomic Energy Commission and used technology developed for naval reactors. The knowledge and the materials and the skilled personnel all came, directly or indirectly, from the weapons programs. This was true in every country that developed nuclear power. The civilian atom and the military atom were born together, and they grew up together, and they have never been fully separable. That does not mean that nuclear power is simply a cover for weapons programs. It is not. The vast majority of nuclear plants built since the 1950s have been purely civilian in their operation, producing electricity and nothing else. But the historical connection is real, and it shaped how the technology developed, how it was regulated, and how it was perceived by the public. Let me also say a little more about the scale of these early plants, because it helps to understand how much has changed. Obninsk produced 5,000 kilowatts. Calder Hall produced about 200,000 kilowatts. Shippingport produced 60,000 kilowatts. To put those numbers in perspective, a modern large nuclear plant produces around 1 million kilowatts or more, enough to power a major city. The early plants were experiments, demonstrations, proofs of concept. They were built to show that it could be done, not to compete economically with coal or oil. And in that sense, they succeeded. They proved that a nuclear reactor could run steadily for months or years, producing reliable electricity without burning fossil fuels. They proved that the chain reaction could be controlled, contained, and harnessed for peaceful purposes. They proved that the atom, which had first been split in a Berlin laboratory in 1938, which had first been made to sustain a chain reaction in a Chicago squash court in 1942, which had first been used as a weapon in 1945, could also light a living room, run a refrigerator, power a factory. That was a significant thing. It was a turning point in the long story we have been walking through. Now, as we come to the end of this section, I want to give you a simple image to carry into the next part of our journey. Imagine it is evening, and you are standing outside a small house in one of the towns near Obninsk, or Calder Hall, or Shippingport, sometime in the late 1950s. The sun has gone down, the sky is dark, and you see, through the window of that house, a light come on. A simple electric light, a bulb in a lamp on a table. Someone inside has flipped a switch, and the light has come on, and the electricity that powers that light is coming from a nuclear reactor a few miles away. The chain reaction that started with a neutron hitting a uranium nucleus, splitting it, releasing energy and more neutrons, is now, after passing through heat exchangers and steam pipes and turbine blades and generators and transformers and power lines, ending up as a warm glow in a quiet room. The whole invisible cascade, from the atomic nucleus to the lit bulb, is complete. That is what these first plants achieved. Not just a technical milestone, but a connection, a thread linking the smallest things in the universe to the most ordinary moments of human life. The light in the window, the hum of the refrigerator, the radio playing softly in the kitchen, all of it powered, for the first time, by the energy that holds the atom together. As you drift now, let that image be your companion. A quiet evening, a small house, a light coming on in a window, and somewhere in the distance, a reactor core, humming steadily to itself, splitting atoms one by one, sending out its invisible energy into the grid. The first lights of the nuclear age were modest, but they were real, and they changed the world. And that is where we will pick up the story next time, with the spread of those lights, the growing years when nuclear power expanded across the globe, when the optimism of the 1950s carried forward into the 1960s and 1970s, before the accidents came and changed everything. But that is for later. For now, just rest with the light in the window. Just breathe, just drift. The first lights of the nuclear age were modest, but they were real, and they changed the world. Now, before we walk further into the history, before we visit the years of expansion and the accidents that shifted public trust, it is time to pause and understand more clearly how these machines actually work. Not in every technical detail, because that would fill libraries, but in plain, simple terms. A nuclear power plant is, at its heart, a way to boil water. That is the central idea, and it is worth holding on to. A nuclear power plant boils water. The water turns to steam. The steam spins a turbine. The turbine turns a generator. The generator produces electricity. That sequence, from boiling water to electricity, is the same in a coal plant, an oil plant, a natural gas plant, and a nuclear plant. The only difference is what provides the heat to boil the water. In a coal plant, it is burning coal. In a nuclear plant, it is splitting atoms. So let us begin with the splitting of atoms, the process we have been calling fission. We have talked about it several times already in this long story, but now we need to understand it as an ongoing, controlled process, a steady source of heat rather than a sudden release of energy. The fuel in most nuclear reactors is uranium, specifically an isotope of uranium called uranium-235. Remember that isotopes are versions of an element with different numbers of neutrons in the nucleus. Uranium-235 has 92 protons and 143 neutrons. It is relatively rare in nature, making up less than 1% of natural uranium, so the fuel used in many reactors has been processed to increase the concentration of this isotope. This processing is called enrichment, and it is a complex and expensive industrial process, but the result is uranium fuel with a higher proportion of the atoms that can be split. When a uranium-235 nucleus is struck by a slow-moving neutron, it absorbs that neutron and becomes, for a tiny fraction of a second, uranium-236. This nucleus is extremely unstable. It almost immediately splits, or fissions, into two smaller nuclei. These are typically elements from the middle of the periodic table, like barium and krypton, the same ones that Hahn and Strassmann found in their Berlin laboratory in 1938. These two smaller nuclei are called fission products. Along with the fission products, the splitting also releases a large amount of energy, mostly in the form of heat, and it releases, on average, 2 or 3 free neutrons. These neutrons fly away from the fission site at high speed. If one of them strikes another uranium-235 nucleus, that nucleus can fission as well, releasing more heat and more neutrons. This is the chain reaction, the same process that Fermi first controlled in the squash court under the stands of Stagg Field. Now, if every fission produced exactly one neutron that went on to cause another fission, the chain reaction would be perfectly steady. The number of fissions per second would stay constant, and the heat output would stay constant. This is called criticality, and it is the condition that a nuclear reactor is designed to maintain during normal operation. If fewer than one neutron per fission goes on to cause another fission, the chain reaction will slow down and eventually stop. This is called subcriticality. If more than one neutron per fission goes on to cause another fission, the chain reaction will grow, and the heat output will increase. This is called supercriticality. A nuclear reactor is designed to operate exactly at the critical point, where the chain reaction is self-sustaining but not growing. Achieving and maintaining this balance is the central task of operating a nuclear reactor. To control the chain reaction, reactors use materials that absorb neutrons. These materials are formed into rods, called control rods, that can be inserted into or withdrawn from the reactor core. When the control rods are fully inserted, they absorb so many neutrons that the chain reaction cannot be sustained. The reactor is shut down, subcritical. When the control rods are partially withdrawn, fewer neutrons are absorbed, and the chain reaction can proceed at a steady rate. If the operators want to increase the power output, they withdraw the control rods slightly, allowing more neutrons to find uranium nuclei and cause fissions. If they want to decrease the power, they insert the control rods a little further, absorbing more neutrons and slowing the reaction. The control rods are typically made of materials like cadmium, boron, or hafnium, all of which are very good at capturing neutrons. In an emergency, the control rods can be inserted rapidly, by gravity or by spring pressure or by hydraulic force, to shut the reactor down quickly. This is called a scram, a term whose origin is debated, but which has been part of the nuclear lexicon since the earliest days. But there is more to it than just control rods. The neutrons released by fission are moving very fast, and fast neutrons are not easily captured by uranium-235 nuclei. To keep the chain reaction going, the neutrons need to be slowed down. This slowing down is done by a material called a moderator. The moderator is a substance that neutrons bounce off without being absorbed, losing a little energy with each bounce until they reach the right speed to be captured by a uranium-235 nucleus and cause another fission. In the early Chicago pile, the moderator was graphite. Many later reactors use ordinary water as both a moderator and a coolant. The hydrogen atoms in water are very effective at slowing neutrons because they have roughly the same mass as a neutron, which means the neutron transfers a lot of its energy in each collision. Think of it like two billiard balls colliding. When one strikes another of equal mass, the energy transfer is efficient. That is why water makes a good moderator. Some reactors use heavy water, which is water where the hydrogen atoms have an extra neutron in their nucleus, making them deuterium rather than ordinary hydrogen. Heavy water is an even better moderator than ordinary water because it absorbs fewer neutrons, which means the reactor can use natural uranium fuel without enrichment. But heavy water is expensive to produce. Most of the world's power reactors use ordinary water, which is cheap and plentiful, but they need enriched uranium fuel to compensate for the neutrons that the ordinary water absorbs. These design choices, the choice of moderator and coolant and fuel type, define the different kinds of reactors that were built during the growing years, the subject of our next section. So we have a reactor core, which contains the uranium fuel, the moderator, and the control rods. The chain reaction is running, steady and controlled. Heat is being produced. Now we need to get that heat out of the reactor and use it to make electricity. The heat is carried away by a coolant, a fluid that circulates through the reactor core, absorbs the heat from the fission process, and carries it to a place where it can be used. In most reactors, the coolant is water. In some designs, the water is allowed to boil directly in the reactor core, and the steam is sent straight to the turbine. This is called a boiling water reactor. In other designs, the water is kept under high pressure so that it does not boil, and it is circulated through a heat exchanger called a steam generator. In the steam generator, the hot, pressurized water from the reactor gives up its heat to a separate loop of water, which does boil into steam. This is called a pressurized water reactor. The advantage of the pressurized design is that the radioactive water from the reactor core stays in its own sealed loop and never enters the turbine or the rest of the plant. The steam that spins the turbine is clean, non-radioactive water. Regardless of the design, the steam is produced, and it flows through pipes to the turbine. The turbine is a machine with many blades, arranged in rows on a shaft. The high-pressure steam rushes through the blades, pushing them and causing the shaft to spin. This is the same principle as a windmill, except that the moving fluid is steam rather than air. The spinning shaft of the turbine is connected to a generator, a machine that converts mechanical rotation into electrical current. Inside the generator, magnets spin past coils of wire, inducing an electric current in the wire. That current is then sent out through transformers and power lines to the grid, the network of cables that carries electricity to homes and businesses. After the steam has passed through the turbine, it has lost most of its energy. It is now low-pressure steam, and it needs to be turned back into water so it can be used again. This is done in the condenser, a large heat exchanger where the steam is cooled by contact with pipes carrying cold water from a river, a lake, or a cooling tower. The steam condenses into liquid water, which is then pumped back to the steam generator or the reactor to begin the cycle again. The cooling water, which has absorbed the waste heat from the steam, is either returned to its source slightly warmer, or it is sent to a cooling tower where the heat is released into the atmosphere as water vapor. The large, hourglass-shaped towers that many people associate with nuclear power plants are cooling towers. They are not reactors. They are not emitting radiation. They are simply releasing warm, clean water vapor into the air. You can see similar towers at some coal plants and other industrial facilities. They are part of the cooling system, not part of the nuclear process itself. Now let me go back over the main steps, because repetition is how these ideas settle in. Fission in the reactor core produces heat. The heat is carried away by a coolant, usually water. The hot water either boils directly into steam or transfers its heat to a secondary loop of water that boils into steam. The steam spins a turbine. The turbine spins a generator. The generator produces electricity. The steam is cooled back into water in the condenser. The water is pumped back to the heat source to start again. It is a closed loop for the primary coolant, and often a closed loop for the steam as well. The only thing that leaves the plant is electricity, warm water or water vapor from the cooling system, and a very small, carefully monitored amount of radiation that is kept well below regulatory limits. This is the quiet engine. It is quiet in the sense that the chain reaction itself makes no sound. There is no combustion, no flame, no roar of burning fuel. The only sounds in a nuclear plant are the hum of pumps, the hiss of steam, the whine of the turbine spinning at high speed. In the control room, it is quieter still. Operators sit at panels, watching screens and gauges, logging data, making small adjustments. The reactor core, where all the energy is being released, is sealed inside a thick steel pressure vessel, which is itself surrounded by a reinforced concrete containment building, designed to hold in any radioactive material that might escape in an accident. The containment building is the dome-shaped structure that is visible from outside. It is a passive safety feature, a barrier that stands between the reactor and the outside world. The fuel itself is arranged in a precise geometry inside the core. Uranium is formed into small ceramic pellets, each about the size of a fingertip. These pellets are stacked inside long metal tubes called fuel rods. The fuel rods are bundled together into assemblies, and the assemblies are arranged in a grid inside the reactor vessel. The spacing is carefully calculated to ensure that the neutrons can travel from one rod to another, that the coolant can flow freely between them, and that the control rods can slide in and out to adjust the reaction. The whole core is a piece of precision engineering, designed and tested and inspected to exacting standards. One of the most important concepts in reactor safety is something called negative feedback. In a well-designed reactor, if the temperature rises, the chain reaction naturally tends to slow down. This is because the moderator becomes less effective at higher temperatures, or the fuel expands slightly and becomes less dense, or other physical effects come into play. This means that the reactor is inherently stable. If it starts to get too hot, the physics pushes back, reducing the reaction rate. Operators do not have to intervene constantly to prevent a runaway. The reactor, by its nature, tends to settle at a steady power level. Control rods are used for fine adjustments, for starting up and shutting down, and for long-term compensation as the fuel is gradually used up. But the basic tendency of the reactor, in normal conditions, is to be self-regulating. This is a crucial design principle, and it is one of the reasons that nuclear accidents are rare. When they do happen, as we will see in later sections, it is usually because multiple safety systems failed at once, or because the reactor design lacked this inherent stability, or because human operators overrode the automatic safety features. Now let me say a word about what happens to the fuel over time. As a reactor operates, the uranium-235 atoms are gradually consumed. They fission and become smaller atoms, the fission products. Some of these fission products are unstable and radioactive. They decay over time, releasing more heat and radiation. This is why a reactor cannot simply be turned off like a light switch. Even after the control rods are inserted and the chain reaction stops, the fission products in the fuel continue to decay and produce heat. This is called decay heat. It is a small fraction of the reactor's operating power, but it is still significant. If the cooling system fails after shutdown, the decay heat can build up and damage the fuel. This is what happened at 3 Mile Island, at Chernobyl, and at Fukushima, as we will discuss in their own sections. Managing decay heat is one of the central challenges of reactor safety. The plants are designed with multiple backup cooling systems, emergency generators, batteries, and other measures to ensure that the fuel can always be kept cool, even if the main power supply is lost. The spent fuel, the fuel that has been used up and removed from the reactor, is still highly radioactive. It is stored, initially, in deep pools of water at the plant site. The water cools the fuel and provides shielding from the radiation. After several years, the fuel has cooled enough that it can be transferred to dry storage, typically large concrete and steel casks that sit on a secure pad at the plant. The long-term question of what to do with this spent fuel, where to put it permanently so that it will be safe for the thousands of years it remains radioactive, is one of the unresolved challenges of nuclear power. We will return to that question in the final section of our story. For now, it is enough to know that the spent fuel is being stored, safely but temporarily, at reactor sites around the world, while the debate about a permanent solution continues. So this is how the quiet engine works. It is, in a way, a very simple machine. Heat from splitting atoms boils water. Steam spins a turbine. A generator makes electricity. Everything else, the control rods and the moderators and the coolant loops and the containment buildings and the backup safety systems, is in service of that simple sequence. The complexity comes from the need to do it safely, to control a process that releases enormous energy from a very small amount of material, to manage the radiation and the decay heat and the spent fuel, to ensure that the invisible chain reaction never escapes its carefully designed boundaries. The quiet engine is quiet because it is contained, because the forces at its heart are held in balance by layers of engineering and monitoring and human attention. When those layers fail, the quiet can be broken. We will come to those moments soon, but for now, as you lie here in the dark, let the quiet engine hum its steady hum. Picture the core, glowing faintly blue under deep water, the Cherenkov radiation that is the optical equivalent of a sonic boom. Particles moving faster than light can travel in water. Picture the steam pipes, insulated and silent, carrying their invisible heat. Picture the turbine spinning at 3,000 revolutions per minute, or whatever speed matches the electrical grid it serves. Picture the generator, turning motion into current, sending electrons down copper wires, through transformers, through substations, through streetlights, to the lamp beside your bed, to the clock on your nightstand, to the quiet dark around you. All of it connected, all of it part of the same chain, from the neutron to the nucleus, to the turbine to the light. That is the quiet engine. That is how it works. And that is enough to know for now. The quiet engine was proven. The first lights had come on in Obninsk, at Calder Hall, at Shippingport. And what followed was a period of steady, confident expansion. The 1960s and 1970s were the years when nuclear power grew from a set of small demonstration plants into a major industry, one that promised to provide a significant share of the world's electricity for generations to come. This was the era of big builds, of construction cranes on the horizon, of concrete domes rising against the sky, of control rooms being wired and tested and commissioned. It was a time of general optimism about the technology, a sense that the atom had been successfully turned from a weapon into a tool, and that the tool was now ready for widespread use. To understand the scale of this expansion, it helps to look at the numbers, but we will look at them slowly and in plain words. In 1960, there were only a handful of nuclear power plants operating in the world, and their total electrical output was small, just a few 100,000 kilowatts spread across a few sites. By 1970, the number of plants had grown significantly, and the total nuclear generating capacity worldwide had reached roughly 20 million kilowatts. By 1980, just 10 years later, that number had multiplied more than 10 times, to over 200 million kilowatts. Hundreds of reactors were operating in countries across North America, Europe, and Asia. The United States led the way in total numbers, but France, the Soviet Union, the United Kingdom, Japan, Canada, and West Germany all built substantial nuclear fleets. Nuclear power was no longer an experiment. It was a normal part of the electrical grid in many of the world's largest economies. This growth did not happen by accident. It was the result of deliberate government policies. In country after country, governments decided that nuclear power was worth supporting, worth subsidizing, worth building into the long-term planning for energy. The reasons varied from place to place. For some countries, like France and Japan, the motivation was energy independence. Neither country had large domestic supplies of oil or coal, and both had experienced the vulnerability of relying on imported fossil fuels. The oil shocks of the 1970s, when the price of oil spiked and supplies were disrupted, made energy independence seem not just desirable but urgent. Nuclear power, once the plants were built, ran on uranium, which could be stockpiled for years and which came from politically stable countries like Canada and Australia. For a country worried about being cut off from Middle Eastern oil, a nuclear plant was a form of insurance. For other countries, the motivation was economic. Nuclear power plants were expensive to build, but relatively cheap to run. The fuel costs were a small fraction of the total operating cost, unlike a coal or gas plant where fuel was the largest expense. This meant that once a nuclear plant was built and paid for, it could produce electricity at a stable, predictable cost for decades. Utilities liked this predictability. Governments liked the fact that nuclear plants created high-skilled jobs and supported domestic industries. The construction of a single large nuclear plant required thousands of workers, millions of tons of concrete, miles of pipe and cable, and components manufactured in factories across the country. It was a major industrial undertaking, and it generated economic activity far beyond the plant site itself. And for some countries, there was also a less openly stated motivation. The civilian nuclear program provided a cover, a pool of trained personnel, and a domestic source of fissile material that could, if necessary, be directed toward weapons. This was the dual-use nature of the technology that we have touched on before. Not every country with nuclear power pursued weapons, of course. Most did not. But the capability was there, latent in the enrichment plants and the spent fuel reprocessing facilities and the trained workforce. This added a geopolitical dimension to the spread of nuclear power. The International Atomic Energy Agency, founded in 1957, was tasked with monitoring civilian programs to ensure they were not being diverted to military use. It was a delicate balancing act, and it mostly worked, though there were cases where countries used civilian technology as a stepping stone toward weapons capability. Now let me describe the two main types of reactors that were built during these growing years, because they still dominate the world's nuclear fleet today. Both are types of what are called light water reactors. Light water is just ordinary water, the kind that comes out of a tap, as opposed to heavy water, which has a different form of hydrogen. Light water reactors use ordinary water as both the coolant and the moderator. The two main variants are the pressurized water reactor and the boiling water reactor. We touched on these briefly in the last section, but now we can give them a little more space. The pressurized water reactor, often shortened to PWR, keeps the primary coolant water under very high pressure, about 150 times atmospheric pressure, so that it does not boil even when heated to temperatures well above the normal boiling point of water. This hot, pressurized water circulates through the reactor core, absorbs the heat from the fission process, and then flows through a heat exchanger called a steam generator. In the steam generator, the heat is transferred to a separate loop of water, which is at lower pressure and does boil into steam. The steam then drives the turbine. The advantage of this design is that the radioactive primary coolant never leaves the containment building and never comes into contact with the turbine. The steam that goes to the turbine is clean, non-radioactive water. This makes maintenance of the turbine and the rest of the plant much simpler and safer. Most of the world's nuclear power plants are pressurized water reactors. They were the dominant design in the United States, France, Japan, and many other countries. The boiling water reactor, often shortened to BWR, takes a different approach. In this design, the water is allowed to boil directly in the reactor core. The steam produced in the core is sent straight to the turbine, without an intermediate steam generator. This simplifies the plant design, because there is one less loop of water and one less large piece of equipment. But it also means that the steam going to the turbine is slightly radioactive, because it has been in direct contact with the fuel. The turbine and the associated piping must be shielded, and maintenance is more complicated because of the radiation. boiling water reactors were built in significant numbers, particularly by General Electric in the United States, and they remain the second most common type of power reactor in the world. Both of these designs, the PWR and the BWR, are light water reactors. They use ordinary water, they use enriched uranium fuel, and they are based on technology originally developed for naval propulsion, particularly for submarines and aircraft carriers. The United States Navy's nuclear propulsion program, led by Admiral Hyman Rickover, was a major driver of light water reactor technology. Rickover was a demanding and meticulous leader who insisted on rigorous engineering standards, extensive testing, and a culture of safety that became a model for the civilian industry. Many of the engineers and operators who staffed the early civilian plants had been trained in the naval program, and they brought Rickover's exacting standards with them. This is one reason why the early decades of nuclear power were relatively free of serious accidents. The technology was new, but the people running it were experienced and disciplined. Other countries developed their own reactor designs. Canada, with its abundant natural uranium and lack of domestic enrichment facilities, developed the CANDU reactor, which uses heavy water as both moderator and coolant. Heavy water absorbs very few neutrons, which means the reactor can run on natural uranium without enrichment. The CANDU design also allows the reactor to be refueled while it is operating, without shutting down, which improves efficiency. The United Kingdom continued to build gas-cooled reactors, descendants of the Calder Hall design, using graphite as the moderator and carbon dioxide as the coolant. The Soviet Union built both pressurized water reactors, similar in concept to the Western designs, and a type of graphite-moderated, water-cooled reactor called the RBMK. The RBMK design was a direct descendant of the reactors that had produced plutonium for the Soviet weapons program. It had certain advantages, such as the ability to be refueled online and to produce both electricity and weapons-grade plutonium, but it also had serious safety flaws. Those flaws would become catastrophically apparent in 1986 at a plant called Chernobyl, but that is a story for its own section. During the growing years, the RBMK was simply another reactor type, one of many being built around the world, and its dangers were not widely understood outside a small circle of Soviet experts. The growing years were also a time of scaling up. The early plants, like Shippingport at 60,000 kilowatts, were small. The plants built in the late 1960s and 1970s were much larger, often 1,000,000 kilowatts or more. This scaling up was driven by economics. A larger plant could produce electricity more cheaply per kilowatt than a smaller one, because many of the costs, the control room, the containment building, the security infrastructure, did not increase in proportion to the power output. Bigger was better, or so the logic went. Reactor vendors offered standard designs in a range of sizes, and utilities ordered them with the expectation that electricity demand would continue to grow rapidly, as it had done since the end of the Second World War. The future, it was assumed, would need more and more power, and nuclear plants would provide a large share of it. Public opinion during this period was generally favorable. Nuclear power was seen as modern, clean, and forward-looking. The plants were often depicted in promotional materials as gleaming white structures set in green landscapes, symbols of a technological future that was arriving in the present. Visits to nuclear plants were popular school field trips. The industry ran advertisements touting the benefits of nuclear electricity. Environmental concerns about air pollution from coal plants helped make the case for nuclear as a cleaner alternative. The phrase, "too cheap to meter," was sometimes used, though it was never an official industry slogan. It came from a speech by a government official who speculated that nuclear power might someday be so abundant that it would not be worth the cost of metering individual homes. The phrase stuck in the public imagination, and it contributed to an impression of boundless promise. But not everyone was convinced. Even in the years of rapid growth, there were voices raising concerns. Some scientists questioned whether the long-term waste problem could be solved. Some engineers worried that the scaling up was happening too fast, that the new, larger plants had not been tested as thoroughly as the early demonstration units. Some citizens near proposed plant sites organized to oppose construction, worried about accidents, about the release of warm water into rivers and lakes, about the possibility of radiation exposure. The anti-nuclear movement was small in the 1960s, but grew through the 1970s, drawing energy from the broader environmental movement and from concerns about nuclear weapons. The public trust that had been high in the 1950s and 1960s began to show cracks as the 1970s wore on. There were also economic headwinds. The cost of building nuclear plants rose faster than general inflation. Construction times lengthened. Regulatory requirements increased, particularly after a series of smaller incidents and near misses that did not cause serious harm, but revealed weaknesses in design or operation. Some plants that had been ordered were cancelled before construction began. Others were started but never finished. The era of rapid growth was beginning to slow, even before the accidents that would define the next chapters of our story. By the late 1970s, the nuclear industry was still large, still growing in absolute terms, but the rate of growth had leveled off. The mood was shifting from unqualified optimism to something more cautious. Let me pause here and gather the picture together. The 1960s and 1970s saw nuclear power grow, from a handful of experimental plants to a global industry with hundreds of operating reactors. Two main light water reactor designs, the pressurized water reactor and the boiling water reactor, became the dominant technologies. Countries around the world invested in nuclear power for reasons of energy independence, economic benefit, and in some cases, latent weapons capability. Public trust was generally high, and nuclear power was widely seen as a clean, modern source of electricity for a growing world. But costs were rising, concerns were being raised, and the limits of the technology were becoming clearer. The industry was about to enter a period of testing, and the first major test came at a plant called 3 Mile Island in the state of Pennsylvania, in the United States, in the spring of 1979. That is the threshold we are approaching now. In the next section, we will walk through what happened there, calmly and factually, and we will see how a combination of mechanical failure and human error led to a partial meltdown, and how the containment building held, and how public opinion shifted in ways that are still felt today. But before we cross that threshold, let us stay a little longer in the growing years, in the time when the promise still seemed bright and the risks were still mostly theoretical. Picture a construction site in the early 1970s, somewhere in the American Midwest or the French countryside or the Japanese coast. The ground has been cleared and leveled, the concrete pour for the foundation is underway, a continuous operation that runs day and night, because the foundation must be a single, unbroken slab. The workers wear hard hats and carry clipboards. The engineers study drawings in site trailers. The massive steel components, the reactor pressure vessel, the steam generators, the pressurizer, are being fabricated in factories hundreds of miles away and will arrive on special rail cars or barges. The containment building rises slowly, a dome of reinforced concrete with a steel liner, designed to withstand the pressure of a major accident. The control room is being wired, panel by panel, with miles of cable. Everything is checked, inspected, documented. The standards are high, the budgets are large, the sense of purpose is clear. This plant, when it is finished, will provide electricity for 1 million homes. It will run for 40 years, maybe longer. It will replace coal plants that fill the air with smoke and soot. It will be a quiet engine, humming its steady hum, monitored by skilled operators in a calm, orderly room. This was the vision, and for a while it seemed to be coming true. Now, as you lie here in the dark, let that vision drift through your mind. The cranes against the sky, the concrete domes taking shape, the control rooms being wired, the sense of building something large and lasting, something that would serve generations to come. It was a moment of confidence, a moment when the long arc of this story, from Becquerel's fogged plate to Fermi's pile, to Eisenhower's speech, to the first lights at Obninsk, seemed to be bending toward a bright, steady future. That confidence would be shaken, soon and hard. But that is for later. For now, just rest with the image of the growing years, the years of building, the years of promise. The quiet engine was spreading across the world, and the world was lighting up. Breathe slowly. Let the next part of the journey come when it comes. The growing years were a time of confidence, of cranes against the sky and concrete domes taking shape. That confidence would be shaken, soon and hard. The first major shaking came in the spring of 1979, at a nuclear plant called 3 Mile Island, in the state of Pennsylvania, in the northeastern United States. 3 Mile Island is not a single event with a single cause. It is a story about a series of small things going wrong, one after another, and about the gap between what was happening inside the reactor and what the operators in the control room believed was happening. It is a story about mechanical failure and human error, about confusion and miscommunication, and about how a serious accident can unfold even inside a well-built plant with a strong containment building. And it is also a story about how, in the end, the containment building held. 3 Mile Island is the name of an actual island in the Susquehanna River, a broad, slow-moving waterway that flows through central Pennsylvania. The island is about 3 miles long, hence the name, and it sits roughly 10 miles southeast of the city of Harrisburg, the state capital. On the island, the local utility company had built 2 nuclear reactors, called Unit 1 and Unit 2. Both were pressurized water reactors, the type we discussed earlier, designed by the Babcock and Wilcox Company. Unit 1 had begun operating in 1974. Unit 2 was newer, having started up in late 1978. On the night of March 27, 1979, Unit 1 was shut down for refueling. Unit 2 was running at nearly full power, about 97% of its rated output. The control room was staffed by a crew of trained operators. The instruments showed normal readings. The quiet engine was humming its steady hum. Then, at about 4 o'clock in the morning on March 28th, something went wrong in the part of the plant that is not even nuclear. The secondary loop, the part that carries clean, non-radioactive water from the steam generators to the turbine, experienced a pump failure. A pump that moved water through the secondary loop stopped working, probably because of a blockage or a valve problem. This caused the steam generators to lose their ability to remove heat from the primary loop, the loop that carries water through the reactor core. With the secondary loop not carrying heat away, the temperature and pressure in the primary loop began to rise. The reactor, as designed, responded to this automatically. A relief valve on top of the pressurizer, a large tank that maintains pressure in the primary loop, opened to let off excess pressure. This was supposed to happen. The problem was that when the pressure dropped back to normal, the relief valve did not close. It stuck open, and the operators in the control room did not know it. The instruments in the control room told the operators that the valve had been commanded to close. A light on the panel indicated that the electrical signal had been sent, but the light did not actually show the physical position of the valve. The valve itself was still open. Hot, radioactive water from the primary loop was escaping through the open valve, flowing out into a drain tank on the floor of the containment building. The primary loop was losing coolant. the same coolant that was supposed to keep the reactor core covered and cooled. But the operators, trusting their instruments, did not realize this was happening. At the same time, the emergency core cooling system activated automatically, as it was designed to do. High-pressure pumps began injecting fresh water into the primary loop to make up for the water being lost through the stuck-open valve. This was the correct safety response. But the operators, still not understanding the full picture, saw that the water level in the pressurizer was rising. In their training, a high water level in the pressurizer was a sign that there was too much water in the primary loop, a condition that could cause problems of its own. They did not know that the rising pressurizer level was actually a misleading indicator, a quirk of the particular design of this reactor. Worried about overfilling the system, they reduced the flow from the emergency pumps. They essentially turned down the very system that was trying to save the reactor. With the relief valve stuck open and the emergency cooling reduced, the water level in the reactor vessel itself began to drop. The operators could not see this directly. There was no instrument that told them clearly how much water was in the core. They had to infer it from other readings, and those readings were giving them an incomplete and misleading picture. The top of the reactor core, where the fuel rods were located, became uncovered. The water that was supposed to be cooling the fuel was gone from the upper part of the core. Without cooling water, the temperature of the fuel rods began to rise rapidly. What happened next is what is called a partial meltdown. The zirconium metal cladding that encased the uranium fuel pellets reacted with the steam, producing hydrogen gas. The fuel pellets themselves, made of uranium oxide ceramic, began to overheat and, in some places, to melt. The term meltdown is not a technical term in the strict sense, but it describes the general process of fuel damage that occurs when cooling is lost. In the case of 3 Mile Island, roughly half of the reactor core melted. The molten fuel flowed down into the bottom of the reactor vessel, where it eventually cooled and solidified. The reactor vessel itself, a thick steel container, held. It did not rupture. The melted fuel did not escape the vessel. The operators, meanwhile, were still struggling to understand what was happening. The control room was filling with alarms. Hundreds of warning lights and audible signals were going off, overwhelming the crew with information. The shift supervisor and his team worked through the morning, trying to diagnose the problem, trying to stabilize the plant. At around 6 in the morning, a fresh shift arrived, bringing new eyes to the situation. Gradually, the new shift supervisor began to piece together the true picture: the stuck-open relief valve, the loss of coolant, the uncovered core. Once the problem was understood, the corrective actions were clear. The valve was closed. The emergency cooling was restored. The core was recovered with water. The immediate crisis passed. But the accident was not over in its consequences. The hydrogen gas that had formed inside the reactor vessel had made its way into the containment building. Hydrogen is flammable, and there was a risk of an explosion. This risk lasted for several days, and it caused considerable public concern. In the end, the hydrogen did not explode with enough force to threaten the containment building. The hydrogen bubble was managed, and the danger passed. But during those days, the world was watching. The news media descended on Harrisburg. Conflicting information swirled. There was talk of a massive evacuation. Pennsylvania's governor advised pregnant women and young children to leave the area within a 5-mile radius. The public mood shifted from curiosity to anxiety to something approaching panic. In the end, no evacuation order was ever given for the general population, but the fear was real, and it lingered. The most important fact about 3 Mile Island, the fact that separates it from the accidents we will discuss later, is that the containment building worked. The thick, reinforced concrete dome that surrounded the reactor did what it was designed to do. It held in almost all of the radioactive material. Some radiation did escape, mostly in the form of small amounts of radioactive gases that were vented during the accident and in the days that followed. But the amount of radiation released to the environment was relatively small. Studies conducted in the years after the accident found no measurable increase in cancer rates or other health effects in the surrounding population. The United States Nuclear Regulatory Commission and other agencies concluded that the average radiation dose to people living near the plant was a fraction of the natural background radiation they received every year from the sun, the soil, and the rocks around them. To state it plainly, no deaths were directly attributed to the 3 Mile Island accident. No one in the public was physically harmed in a way that could be measured. The plant workers received higher doses than the public, but even the highest worker exposure was within regulatory limits and did not cause acute radiation sickness. But the physical harm, or lack of it, was only part of the story. The psychological and political impact of 3 Mile Island was profound. The accident shattered the sense of trust that had been built up during the growing years. If a serious accident could happen in a modern American plant, staffed by trained operators and overseen by a strong regulatory body, then perhaps the technology was not as safe as the industry and the government had been saying. The public learned words that had previously been known only to specialists: meltdown, containment, radiation plume, evacuation zone. The fact that the accident unfolded over several days, with confusing and contradictory information coming from the plant and the government, made things worse. People felt they could not trust the authorities to tell them the truth. That erosion of trust was perhaps the deepest damage that 3 Mile Island caused. The accident also had major consequences for the nuclear industry itself. New safety regulations were introduced. Control rooms were redesigned to make instruments clearer and to reduce the risk of operators being overwhelmed by alarms. Emergency planning was strengthened. The Institute of Nuclear Power Operations, an industry self-regulatory body, was founded to share best practices and conduct peer reviews among plants. The Nuclear Regulatory Commission tightened its oversight. No new nuclear plants were ordered in the United States for decades after 3 Mile Island. Some plants that were already under construction were completed. Others were cancelled. The era of rapid growth that had characterized the 1960s and 1970s came to an end. Let me slow down here and walk through the sequence of events one more time, because the story of 3 Mile Island is a story of small failures combining in unexpected ways. A pump in the secondary loop stopped working. That caused the primary loop to overheat and overpressurize. A relief valve opened to release pressure, which was the correct automatic response, but then it stuck open and did not close. The operators did not know the valve was stuck open because their instrument told them the valve had been commanded to close, not whether it had actually closed. Coolant escaped through the open valve. The emergency cooling system activated, but the operators, misled by the pressurizer level reading, reduced the emergency cooling flow because they thought the system was overfilling. The core became partially uncovered, the fuel overheated and partially melted. The zirconium cladding reacted with steam to produce hydrogen. The hydrogen collected in the containment building, causing fears of an explosion. The operators eventually diagnosed the problem, closed the valve, and restored cooling. The core was stabilized. The containment building held. The radiation release was small. No one died. But the psychological and political landscape around nuclear power shifted in ways that are still present today. There is a detail in this story that is worth dwelling on, because it speaks to the human dimension of the accident. The control room operators at 3 Mile Island were not careless or incompetent. They were trained professionals doing their best under extremely difficult conditions. The control room was designed with hundreds of alarms, and during the accident, many of them were going off at once. The operators were flooded with information, but much of it was redundant or unhelpful. The one piece of information they really needed: the actual position of the relief valve, was not directly displayed. The instrument told them what the valve had been told to do, not what it had actually done. This was a design flaw, not an operator error in the simple sense. After the accident, control rooms were redesigned to address this kind of problem. Alarms were prioritized so that the most critical ones stood out. Instruments were added to show the actual state of key components, not just the commanded state. The lessons of 3 Mile Island were learned, and they made the industry safer. The cleanup at 3 Mile Island Unit 2 was a long and difficult process. The damaged reactor was defueled, meaning the melted fuel was removed from the reactor vessel, a job that took years and cost hundreds of millions of dollars. The fuel was shipped to a national laboratory in Idaho for storage and study. Unit 2 never operated again. It remains in a state of monitored storage, its containment building still standing on the island. Unit 1, which was shut down for refueling at the time of the accident and was not damaged, eventually returned to service and continued to operate until 2019, when it was permanently shut down for economic reasons. The island is quiet now, both reactors silent, the control rooms dark. It is a landmark in the history of nuclear power, not because of the damage it caused to the public, which was small, but because of the change it caused in how the public thought about nuclear power. As we come to the end of this section, I want to hold up a single image for you to carry into the dark. The containment building at 3 Mile Island Unit 2, standing intact on its island in the Susquehanna River. It is a large, rounded dome of concrete and steel, unremarkable in appearance, like many other containment buildings around the world. Inside it, the damaged core sits, cooled and stable. The building did its job, the barrier held, the accident was contained, and that fact, that quiet, unglamorous fact, is the reason why 3 Mile Island is remembered as a serious accident, but not a catastrophic one. The difference between a partial meltdown that hurts no one and a disaster that poisons a region is, in large part, the difference between a containment building that holds and one that does not. At 3 Mile Island, it held. The accident at 3 Mile Island was a warning. It showed that serious accidents were possible even in well-regulated modern plants. It showed that operator training and control room design needed to be improved. It showed that communication with the public during an emergency was essential and that getting it wrong could do lasting damage. But it also showed that the defense in-depth approach, the multiple layers of safety systems and barriers, could work. The containment building was the last of those layers, and it did not fail. The world's nuclear industry learned from 3 Mile Island. Safety standards were raised. And for 7 years, there were no major accidents. Then came Chernobyl. But that is a story for the next section. For now, as you lie here in the dark, let the image of the intact containment dome settle into your mind. A serious accident happened. The core melted. The building held. The public was not harmed. It was a close call, a hard lesson, but not a tragedy. Breathe slowly. Let that be enough for now. The next part of the journey will come when it comes. The world's nuclear industry learned from 3 Mile Island. Safety standards were raised, and for 7 years, there were no major accidents. Then came Chernobyl. The story of Chernobyl is different from the story of 3 Mile Island in almost every way. The reactor design was different. The safety culture was different. The cause of the accident was different. The scale of the release of radioactive material was vastly different, and the consequences, both immediate and long-term, were far more severe. This is the most serious accident in the history of nuclear power, and we need to tell it honestly, without drama, without dwelling on graphic detail, but also without minimizing what happened. The Chernobyl nuclear power plant was located in what was then the Soviet Union, in the Republic of Ukraine, near the border with Belarus. The plant sat about 10 miles from the town of Chernobyl, which gave the plant its name, and about 2 miles from the newer city of Pripyat, which had been built to house the plant's workers and their families. Pripyat was a city of about 50,000 people, a model Soviet community, with schools and shops and a large central square. The plant itself had 4 reactors, all of a type called RBMK, which is a Russian acronym that stands for High Power Channel Type Reactor. The RBMK design was a graphite-moderated, water-cooled reactor, a direct descendant of the reactors the Soviet Union had used to produce plutonium for its weapons program. It was a design that had certain advantages. It could be refueled while operating, it could produce both electricity and weapons-grade plutonium, and it was relatively cheap to build. But it also had serious safety flaws that were known to some Soviet scientists and engineers, but were not widely acknowledged or corrected. The most significant of these flaws was something called a positive void coefficient. This is a technical term, but the idea behind it is important. In a properly designed reactor, if the cooling water begins to boil and form steam bubbles, or voids, the chain reaction naturally slows down. This is a form of negative feedback, the self-stabilizing property we discussed earlier. In the RBMK reactor, under certain conditions, the opposite was true. When the cooling water boiled and formed steam voids, the chain reaction would speed up. This is a positive void coefficient, and it means the reactor is inherently unstable. If the water starts to boil, the reactor gets hotter, which makes more water boil, which makes the reactor hotter still. This can lead to a very rapid power surge, faster than human operators or automatic systems can respond to. This design flaw was the root cause of what happened at Chernobyl. The immediate cause was a safety test. On April 25, 1986, the operators at Chernobyl Unit 4 began preparing for a test that had been planned as part of a scheduled shutdown of the reactor. The purpose of the test was to see whether, if the plant lost its normal electrical supply, the spinning down of the turbine could provide enough residual electrical power to run the emergency cooling pumps for the 40 seconds or so it would take for the backup diesel generators to start up. This was a legitimate engineering question, but the test had been poorly planned and was being conducted under conditions that violated safety protocols. The reactor was supposed to be at a steady power level when the test began, but during the preparation, the power dropped too low, and the operators struggled to bring it back up. In the process, they withdrew most of the control rods and disabled several safety systems, including the emergency core cooling system and the automatic shutdown signals that would have tripped the reactor if certain limits were exceeded. They were essentially trying to force the reactor to behave in a way it was not designed to behave, with many of its safety features turned off. The test began in the early hours of April 26th, at about 1:23 in the morning. When the operators shut off the steam to the turbine, the power began to rise. They attempted to insert the control rods to stop the reaction, but the control rod design in the RBMK had another flaw. The tips of the control rods were made of graphite, which acted as a moderator and actually increased the reaction locally as they entered the core, before the boron absorber material further up the rod could begin to absorb neutrons and slow things down. So when the operators pressed the emergency shutdown button, the control rods began to move into the core, and for a brief moment, the reaction surged instead of stopping. In that moment, the power level spiked to more than 100 times the reactor's design maximum. The fuel rods shattered. The pressure tubes that held them ruptured. A massive steam explosion blew the 1,000-ton concrete and steel lid off the top of the reactor. A second explosion followed, probably caused by hydrogen or by the reaction of steam with the hot graphite moderator. The reactor core was now open to the atmosphere. The graphite blocks, now exposed to air, caught fire. That fire burned for days. It was not an ordinary fire. It was a graphite fire, extremely hot and difficult to extinguish, and it carried radioactive material high into the atmosphere. The initial explosions killed 2 plant workers. More than 200 others were hospitalized with acute radiation sickness in the days that followed, and of those, 28 died within the next few months. These are the directly documented deaths from the immediate accident. But the long-term effects, the cancers and other illnesses that may have been caused by the radiation released, are far harder to count, and this is where we need to sit with genuine uncertainty. The radioactive material released by the Chernobyl accident was spread over a wide area by wind and weather. The most heavily contaminated areas were in Ukraine, Belarus, and Russia, but detectable fallout reached as far as Scandinavia, Western Europe, and even North America. The nearby city of Pripyat, with its 50,000 residents, was not evacuated until the day after the accident, about 36 hours after the explosion. When the evacuation order finally came, it was carried out quickly. Buses arrived, and the people were told to bring only what they could carry. They were told they would be able to return in a few days. Most of them never went home again. Pripyat remains a ghost town today, its apartment blocks empty, its Ferris wheel in the amusement park rusted and still, never having been used. The park was scheduled to open just a few days after the accident. It never did. A wider exclusion zone, a circle with a radius of about 19 miles, was established around the plant. More than 100,000 people were permanently relocated from this zone in the months and years that followed. The land inside the zone is still largely uninhabited, though some elderly people eventually returned to their homes despite the restrictions. The zone has become a strange and quiet place, a place where nature has reclaimed the abandoned villages and the wildlife, unaffected by the radiation in ways that scientists are still studying, has flourished in the absence of humans. Wolves and boar and deer, and even rare species like the Przewalski's horse roam the forests. The land is contaminated, but life goes on. The cleanup of the Chernobyl site was an enormous and costly undertaking, carried out by what the Soviet Union called liquidators, workers who were sent into the zone to put out the fire, entomb the reactor, and decontaminate the area. Hundreds of thousands of people eventually served as liquidators over the years. They were soldiers and firefighters and miners and engineers and ordinary citizens, and many of them received radiation doses that were poorly recorded or not recorded at all. The long-term health effects on the liquidators, like the long-term effects on the wider population, are the subject of ongoing study and genuine disagreement among researchers. And this is where the honest record becomes uncertain. How many people died or will die as a result of Chernobyl? The answer depends on how you count, what assumptions you make, and what you consider to be a death caused by the accident. The immediate death toll, as I said, was 31 people, the 2 killed in the initial explosion and the 28 who died of acute radiation sickness in the following months. Beyond that, the numbers become contested. The United Nations Scientific Committee on the Effects of Atomic Radiation, in a major report released in 2008, concluded that the total number of deaths attributable to the radiation from Chernobyl was likely in the range of a few thousand, mostly from thyroid cancer, among people who were children at the time and who drank milk contaminated with radioactive iodine. Other organizations, including some environmental groups, have put forward much higher estimates, in the tens of thousands or even more, based on different models of how radiation affects health at low doses over long periods. There is no scientific consensus on which of these estimates is correct. The models used to predict low-dose radiation effects are based on assumptions that cannot be directly proven or disproven. What can be said plainly is that the Chernobyl accident released a very large amount of radioactive material, that this material caused a measurable increase in thyroid cancer in the affected regions, and that the full long-term health impact may never be known with precision. This uncertainty is not a failure of science. It is a reflection of how difficult it is to trace specific health effects to a specific cause, when those effects may appear decades later and may be indistinguishable from naturally occurring diseases. The reactor itself was eventually entombed in a massive concrete and steel structure called the sarcophagus, built in a hurry under extremely difficult conditions. The sarcophagus was never intended to be a permanent solution, and over time, it began to degrade. In 2016, a new structure called the New Safe Confinement was slid into place over the old sarcophagus. It is an enormous arch, the largest movable land-based structure ever built, tall enough to enclose the Statue of Liberty and long enough to cover a football field. It was built by an international consortium, funded by dozens of countries, and it is designed to contain the radioactive remains for at least 100 years. Inside it, robotic cranes and tools will eventually be used to dismantle the old sarcophagus and the remains of the reactor. That work is ongoing. It will take decades more to complete. The other 3 reactors at the Chernobyl plant continued to operate after the accident. Unit 3, which was in the same building as Unit 4, was shut down in 2000. Units 1 and 2 were shut down earlier. The last reactor at Chernobyl stopped producing electricity more than 2 decades ago. The plant site is now a center for decommissioning and waste management, a long, slow process of cleaning up that will extend far into the future. Let me pause here and gather the threads of this story together. The Chernobyl accident was the worst nuclear accident in history. It was caused by a combination of a flawed reactor design, a poorly planned and executed safety test, and a safety culture that did not encourage operators to question procedures or report concerns. The explosion and fire released a large amount of radioactive material into the environment. The nearby city was evacuated. An exclusion zone was established that remains in place today. The immediate death toll was relatively small, 31 people, but the long-term health effects are the subject of genuine scientific dispute. The cleanup was massive and costly, and it is not yet finished. The reactor is entombed in a vast steel arch, and it will remain hazardous for generations to come. Now I want to do something important. I want to slow down and let you feel the weight of this story without letting it disturb your rest. The purpose of telling you about Chernobyl is not to frighten you. It is to complete the honest record, to show you what can happen when the quiet engine is not quiet, when the barriers fail and the chain reaction escapes its bounds. Chernobyl is not representative of nuclear power as a whole. It was a specific failure of a specific design, operated under specific conditions that do not exist anywhere else in the world today. The RBMK reactors that remain in operation have been modified to reduce the positive void coefficient and improve safety. No reactor with the same combination of design flaws will ever be built again. The lessons of Chernobyl were learned at a terrible cost, and they have been applied. But the accident also changed how the world thought about nuclear power. If 3 Mile Island shook public confidence in the West, Chernobyl shattered it in the East and deepened the doubts everywhere. The idea that a nuclear accident could contaminate a whole region, making it uninhabitable for decades, was no longer theoretical. It had happened. The invisible danger of radiation, the fact that it cannot be seen or smelled or tasted, made it particularly frightening to the public. The secrecy and denial of the Soviet government in the first days after the accident, when officials in Moscow downplayed the severity and delayed evacuations, eroded trust in a way that has never fully healed. Chernobyl was not just a nuclear accident. It was a political event, a moment that exposed the failures of the Soviet system and contributed, in its own way, to the reforms that would eventually lead to the dissolution of the Soviet Union 5 years later. As you lie here in the dark, let me give you an image to hold, one that is honest but not harsh. Picture the new safe confinement, the great steel arch, sliding slowly into place over the ruined reactor. It moved on rails, pushed by hydraulic jacks, at a speed so slow you would have to watch for a long time to see it move at all. It took days to travel the few hundred yards from its construction site to its final position. And now it sits there, still and silent, a vast, clean curve of metal against the flat Ukrainian landscape. Inside it, the old sarcophagus, cracked and crumbling, still contains the melted core, the graphite blocks, the radioactive dust. Outside it, the exclusion zone stretches for miles, a place of abandoned villages and thriving wildlife, a landscape that is both contaminated and, in its strange way, at peace. The arch is designed to last a century. It is a monument to the accident, but also to the response, to the slow, patient work of making safe what can be made safe. It is not a solution, it is a holding action, a way of containing the problem until future generations can figure out something more permanent. That is, in a way, the story of nuclear power itself. It is a technology that demands long-term thinking, that forces us to consider consequences that stretch far beyond our own lifetimes. And the honest truth is that we are still learning how to do that. Let the arch settle into your mind. Let it stand there, quiet and silver-gray, under the wide Ukrainian sky. It holds no danger for you, lying here in the dark. It is just a structure, just a piece of engineering, doing its slow, silent work. The accident happened. The consequences were real. The uncertainty about the long-term effects is real. And the response, the arch, the exclusion zone, the ongoing cleanup, is also real. All of these things are true at once. We can hold them all without being overwhelmed by them. Breathe slowly. The story is nearly done. The next part of the journey will bring us to the most recent accident, at Fukushima, and then to the present day. But that is for later. For now, just rest, just breathe. Just let the arch stand silent in your mind. The story is nearly done. The arch stands silent in your mind. And now we turn to the most recent of the three major accidents, the one at the Fukushima Daiichi nuclear power plant in Japan. This accident is different from both 3 Mile Island and Chernobyl in its causes and in its nature. It was not primarily a failure of reactor design, though design choices played a role. It was not primarily a failure of operator training or safety culture, though those too were factors in the broader story. The Fukushima accident was, at its root, a natural disaster that overwhelmed the defenses that had been built to protect the plant. It is a story about the power of the Earth itself, about the limits of human foresight, and about what happens when the unthinkable becomes real. Japan is a country that lives with earthquakes. The Japanese archipelago sits on the boundary of several tectonic plates, the great sections of the Earth's crust that float on the molten mantle below and grind against each other in slow, irresistible motion. Earthquakes are a fact of life in Japan, as ordinary in their way as hurricanes are in the Caribbean or tornadoes are in the American Midwest. Japanese building codes are among the strictest in the world. Japanese engineers have developed sophisticated techniques for making structures that can sway and flex without breaking. The Fukushima Daiichi plant, located on the Pacific coast of Fukushima Prefecture, about 150 miles north of Tokyo, was designed with earthquakes in mind. It had survived many of them over the years, including some quite strong ones, without serious incident. The plant was a collection of 6 boiling water reactors, the type we discussed earlier, where water is allowed to boil directly in the reactor core and the steam is sent to the turbines. The reactors had been built starting in the late 1960s, and the oldest ones, Units 1 through 4, were of an earlier design than the newer Units 5 and 6. All of them were housed in containment buildings, and all of them had multiple backup safety systems. The plant sat right on the edge of the ocean, which was convenient for drawing in the enormous amounts of cooling water that a nuclear plant requires. A seawall protected the plant from the waves. The seawall was about 19 feet high, which was thought to be sufficient. It was not. On March 11, 2011, at 2:46 in the afternoon local time, an enormous earthquake struck off the coast of Japan. It was a magnitude 9 earthquake, one of the most powerful ever recorded anywhere in the world. The shaking lasted for 6 minutes, an eternity in earthquake terms. The ground moved, buildings swayed, roads cracked, and the reactors at Fukushima Daiichi did what they were designed to do. They detected the shaking and automatically inserted their control rods, shutting down the chain reaction. This is called a scram, the rapid shutdown we mentioned earlier. All 3 reactors that were operating at the time, Units 1, 2, and 3, shut down successfully. Units 4, 5, and 6 were already shut down for maintenance. The fission stopped. The chain reactions were over. But remember what we discussed in the section about how the quiet engine works. Even after the chain reaction stops, the fuel continues to produce heat from the decay of the fission products. This decay heat is a small fraction of the reactor's operating power, but it is still significant. It must be removed by cooling water, or the fuel will overheat. Normally, the cooling water is circulated by pumps that run on electricity from the grid or from backup diesel generators. When the earthquake struck, it knocked out the electrical grid connections to the plant. The backup diesel generators started automatically, as they were designed to do. For a few minutes, everything seemed to be working. The reactors were shut down, the generators were running, the cooling pumps were operating, the quiet engine was still quiet, still under control. Then the tsunami arrived. The earthquake had occurred under the seabed, and it had displaced a huge volume of water. That water, traveling at hundreds of miles per hour across the open ocean, reached the Japanese coast about 40 minutes after the shaking began. At Fukushima Daiichi, the waves that came over the seawall were not 19 feet high. They were more than 40 feet high, perhaps as much as 50 feet in some estimates. They swept over the seawall, across the plant site, and into the buildings that housed the emergency diesel generators. The generators were in basements or at ground level because the designers had not anticipated a tsunami of this size. The water flooded them. They stopped. The pumps that were supposed to cool the reactors lost power. The batteries that were supposed to provide backup power for instruments and controls were also flooded or depleted. The plant was now in a state called station blackout, a complete loss of all alternating current power. Without power, the cooling water could not circulate. The decay heat in the reactor cores began to build. What happened over the next several hours and days was a slow, desperate struggle. The workers at the plant, under conditions that were chaotic and dangerous, tried to restore cooling by any means available. They brought in portable generators. They used fire trucks to pump water into the reactors. They vented the containment buildings to release pressure, which allowed some radioactive material to escape. They faced aftershocks, additional tsunami warnings, and the constant threat of further explosions. Despite their efforts, the water levels in the reactors dropped. The fuel rods became uncovered. They overheated. The zirconium cladding reacted with steam to produce hydrogen, the same process that had occurred at 3 Mile Island. The hydrogen built up in the upper parts of the reactor buildings, and in 3 of the units it exploded. These were not nuclear explosions. They were chemical explosions, hydrogen gas igniting in air. But they blew the roofs and walls off the reactor buildings, scattering debris and releasing more radioactive material to the environment. In the end, 3 reactor cores at Fukushima Daiichi suffered meltdowns. The fuel melted and fell to the bottom of the reactor pressure vessels, and in at least some of the units, it likely melted through the vessels and onto the concrete floor of the containment building. The exact location and condition of the melted fuel is still not fully known. because the radiation levels inside the containment buildings are too high for people to enter and inspect directly. Remote-controlled robots have sent back images and data, but the full picture is still being assembled, piece by piece, more than a decade later. The release of radioactive material from Fukushima was substantial, though much less than at Chernobyl. The Japanese government established an evacuation zone around the plant, eventually extending to a radius of about 12 miles. More than 150,000 people were evacuated from their homes. Many of them have never returned. Some areas remain too contaminated for permanent residence, though radiation levels have dropped significantly over time. The cleanup of the land, the removal of contaminated soil and vegetation, has been a massive and expensive undertaking, and the decommissioning of the damaged reactors themselves is a project that is expected to take decades, perhaps as long as 40 years or more, from start to finish. Unlike Chernobyl, there were no deaths from acute radiation sickness at Fukushima. No plant workers died from radiation exposure, though several were injured and some received doses that increased their long-term cancer risk. The evacuation itself, however, caused significant harm. More than 2,000 people died as a result of the evacuation process, mostly elderly people and hospital patients whose health could not withstand the stress and disruption of being moved from their care facilities. These are not deaths from radiation, they are deaths from the response to the accident, and they are part of the honest record. The total death toll directly attributable to the earthquake and tsunami, including those who were lost to the waves, was nearly 20,000 people. The nuclear accident was a small part of a much larger natural disaster, but it is the part that has had the most lasting impact on global energy policy. In the aftermath of Fukushima, countries around the world re-examined their nuclear programs. Germany announced that it would phase out all of its nuclear power plants. Japan shut down all of its reactors and later restarted only a small number under stricter safety regulations. Other countries conducted stress tests, reviewing their plants to see how they would withstand extreme events beyond their original design basis. The concept of a station blackout, the loss of all power, became a central focus of safety planning. New requirements were put in place for backup power sources that could survive flooding, for hardened vents that could be operated without electricity, and for emergency response centers that could function even in the worst circumstances. The Fukushima accident, like the others before it, taught hard lessons. One of those lessons is about the nature of risk. The seawall at Fukushima Daiichi was built to a height that seemed reasonable, based on historical records. The plant's designers knew that tsunamis could happen, but they did not anticipate one of the size that arrived. This is sometimes called a failure of imagination, but it is also a failure of a particular approach to safety. If you design only for the worst event that has happened in the past, you may not be ready for an event that is worse than anything in the historical record. Nature does not respect the limits of human experience. The earthquake that struck Japan in 2011 was far more powerful than any that had been recorded in the region before. The tsunami it generated was far higher than the seawall. The lesson is that when you are dealing with a technology that can cause lasting harm if it fails, you must think beyond what has happened before. You must ask what could happen, even if it seems unlikely. That is a difficult kind of thinking. It is expensive. It is uncomfortable. But Fukushima showed that it is necessary. Let me walk through the sequence one more time, because the shape of the story matters. An earthquake struck. The reactors shut down automatically. The backup generators started. The cooling pumps ran. For a few minutes, everything was working as designed. Then the tsunami came, higher than the seawall, and it flooded the generators. The power failed. The cooling stopped. The cores overheated. The fuel melted. Hydrogen built up and exploded. Radioactive material escaped. The surrounding area was evacuated. The cleanup began, and it continues today. This sequence, from earthquake to tsunami to blackout to meltdown, is a chain of its own, a chain of cause and effect that was set in motion by the largest earthquake in Japan's recorded history. One of the details that stays with you when you study the Fukushima accident is the quiet heroism of the people who stayed at the plant. While the reactors were deteriorating, while the radiation levels were rising, a core group of workers, sometimes called the Fukushima 50, remained on site to try to restore cooling. They worked in darkness, wearing respirators and full-body protective suits, checking gauges, running hoses, venting valves. They knew the risks. Some of them were older workers who volunteered for the most dangerous tasks because they felt they had lived most of their lives already and wanted to spare the younger workers. They worked through the explosions, through the aftershocks, through the fear and the exhaustion. They were not able to prevent the meltdowns, but they did prevent something worse. They kept the situation from spiraling into a complete and catastrophic loss of all cooling to all the spent fuel pools as well, which would have released far more radioactive material. Their work, under conditions that are hard to imagine, was an act of quiet, determined responsibility. It is worth pausing to acknowledge that. The Fukushima plant today is a site of ongoing work. The damaged reactor buildings have been stabilized. The spent fuel has been removed from the pools in some of the units. The contaminated water that was used to cool the melted fuel has been treated to remove most radioactive elements, though a form of hydrogen called tritium remains and cannot be practically separated. After years of study and public debate, the Japanese government decided to release this treated water into the ocean, a process that began in 2023 and will continue for decades. The release is done slowly, under international monitoring, and the scientific consensus is that the radiation dose to people and marine life will be extremely small. But the decision was controversial, and it illustrates the long shadow that nuclear accidents cast. The memory of the accident lingers, and the trust that is needed to accept such decisions is fragile. The full decommissioning of the Fukushima Daiichi plant will take a very long time. The melted fuel must be located, assessed, and eventually removed, a task that is far more difficult than any previous nuclear cleanup. Robots are being developed and tested. New techniques are being invented. The work will extend across generations. The cost will be enormous, certainly many tens of billions of dollars, perhaps more. The plant site will remain an active industrial zone, a place of careful, quiet work, for decades to come. It is not an exclusion zone in the same way Chernobyl is. Many of the surrounding towns have been reopened and are being rebuilt, though the population has not fully returned. Life is resuming, slowly, at the edges of the accident, but the plant itself remains a place of hazard and of patient, persistent effort. Now, as we near the end of this section, I want to place Fukushima in the context of our long story. We began with a fogged photographic plate in a drawer in Paris in 1896. We walked through the slow uncovering of the atom's structure, the splitting of the nucleus, the first controlled chain reaction under a football stadium. We faced the weight of the bombs and the turn toward peaceful use. We saw the first lights come on at Obninsk, Calder Hall, Shippingport. We learned how the quiet engine works, and we watched it spread across the world in the growing years. Then came the accidents, 3 Mile Island, where the containment held and no one was harmed. Chernobyl, where a flawed design and a reckless test led to an explosion and a lasting scar on the landscape. And now Fukushima, where the Earth itself overwhelmed the defenses and 3 cores melted. Each accident was different. Each one taught different lessons. Each one shaped the way the world thinks about nuclear power. Fukushima, like the others, is not the end of the story. Nuclear power continues. The quiet engine still hums in many places. The debate about its future is ongoing, and it is a debate that touches on deep questions about risk and safety, about energy and the environment, about the legacy we leave to future generations. In the next and final section of our long walk, we will bring the story up to the present day, and then let it drift off into the quiet of the night. We will look at where nuclear power stands now, at the unresolved question of waste, at the new designs being tested, and at the long arc that stretches from that first glowing plate to the lit houses of today. But that is for later. For now, let the image of the Fukushima plant settle into your mind. The sea beyond the seawall, calm now. The damaged reactor buildings, their roofs blown off but their containment vessels intact. The workers, still there, still working, still managing the slow, patient task of making the site safe. The quiet engine was quiet no longer, for a time. But the quiet has returned in its own way. The work continues, the lessons are still being absorbed, and the story goes on. The story goes on. The quiet engine still hums in many places, and the debate about its future is ongoing. We have walked a long road together tonight, from a fogged photographic plate in a Paris drawer to a chain reaction under a Chicago football stadium, from the first lights at Obninsk to the accidents that changed how the world thinks about nuclear power. Now, in this final section, we will bring the story up to the present moment and then let it settle, softly, into the quiet of the night. This is not a conclusion, because the story is not concluded. It is a resting point, a place to pause and look around before drifting off. As of today, nuclear power provides about 10% of the world's electricity. That is a significant share, though it is smaller than what many people in the growing years of the 1960s and 1970s imagined it would become. There are roughly 440 nuclear power reactors operating in more than 30 countries. The largest fleets are in the United States, France, China, Russia, and South Korea. Some countries, like France, rely heavily on nuclear power. In France, about 70% of the country's electricity comes from nuclear plants, the highest share of any nation. Other countries, like Germany and Italy, have decided to phase out their nuclear programs entirely. Still others, like China and India, are building new reactors at a steady pace, adding nuclear capacity to meet growing demand for electricity without burning more coal. The global picture is mixed. It is not a story of simple growth or simple decline. It is a patchwork of different choices, different policies, different attitudes toward risk and reward. The debate about nuclear power has been renewed in recent years, partly because of a growing concern about climate change. Nuclear plants, once they are running, produce almost no carbon dioxide. They do not contribute to the warming of the atmosphere in the way that coal and natural gas plants do. For people who are worried about the long-term stability of the climate, this is a powerful argument in favor of nuclear power. It is a source of large-scale, reliable electricity that does not depend on the weather, unlike solar panels and wind turbines, and that does not emit greenhouse gases, unlike fossil fuels. But the arguments against nuclear power have not gone away. The risk of accidents, however small, is real. The question of what to do with the spent fuel remains unresolved. The cost of building new plants is high, and the time it takes to build them is long. These are not imaginary concerns. They are genuine parts of the calculation that every country and every community must make. Let me talk for a moment about the waste question, because it is one of the most persistent and difficult issues in the whole nuclear story. When fuel is removed from a reactor, it is intensely radioactive. It contains fission products, the smaller atoms created when uranium splits, and it contains transuranic elements, atoms heavier than uranium that are created when uranium captures neutrons without fissioning. Some of these materials remain dangerously radioactive for thousands of years. The question is, where do you put them for all that time so that they will never harm anyone? The current practice, almost everywhere in the world, is to store the spent fuel at the reactor sites where it was produced. First, it goes into deep pools of water, where the water cools the fuel and shields the radiation. After several years, when the heat and radiation have decreased somewhat, the fuel can be moved into dry casks, which are large containers made of concrete and steel. These casks sit on concrete pads at the plant site, surrounded by fences and monitored by security systems. They are safe for now. The engineers who designed them will tell you that they can last for a century or more without problems. But a century is not thousands of years. A century is not the span of time that the waste remains hazardous. The dry casks are a temporary solution, a way of holding the problem until something more permanent can be arranged. The widely accepted scientific consensus is that the best long-term solution is a deep geologic repository, a facility built far underground in a stable rock formation where the waste can be placed and sealed and left to decay over geologic time. Several countries have pursued this idea. Finland has built a repository at a site called Onkalo on the country's west coast. It is a network of tunnels carved into solid granite, more than 1,400 feet below the surface. The plan is to seal the waste in copper canisters, embed them in bentonite clay, and eventually, after a century or so of monitoring, backfill the tunnels and close the facility for good. Finland is the first country to have actually begun construction of such a repository. Sweden is not far behind. Other countries, including the United States, have spent decades studying possible sites, but political opposition and public concern have repeatedly stalled progress. The technical challenge of building a repository is solvable. The political and social challenge of deciding where to put it has proven much harder. So the waste sits for now in pools and dry casks at reactor sites around the world. It is managed, it is monitored, it is safe at this moment, but it is a problem that we are passing on to future generations, and that is a weight that the story of nuclear power carries with it. To be honest about nuclear power is to acknowledge this weight. It is not a reason to abandon the technology, nor is it a problem that can be wished away. It is simply a fact of the record, a part of the long arc that stretches from the splitting of the atom to the present day. Now let me turn to something newer, something that is still being tested and developed. The large nuclear plants that were built in the growing years, the ones with their massive concrete domes and their output of 1 million kilowatts or more, are not the only way to build a reactor. There is a different approach, one that uses smaller, simpler designs that can be built in factories and assembled on site, rather than being custom-built from the ground up. These are called small modular reactors, often shortened to SMRs. The idea is to make reactors that produce perhaps 50,000 to 300,000 kilowatts, much less than the giants of the previous generation, but that can be built more quickly, more cheaply, and with fewer opportunities for construction errors. Because they are smaller, they require less upfront investment. Because they are modular, they can be added one at a time as demand grows. And because they use simpler, often passive safety systems, they may be able to shut down safely without any operator action or external power, relying only on natural forces like gravity and convection. Small modular reactors are not a new idea. The United States Navy has been operating small reactors on submarines and aircraft carriers for decades, safely and reliably. But applying the idea to civilian power generation is a more recent development. As of now, there are several companies and research organizations around the world working on SMR designs. Some are based on the light water technology that has been used for decades, just scaled down and simplified. Others use entirely different coolants, like liquid metal or molten salt, which have different safety characteristics and can operate at higher temperatures. A few prototype plants have been built, and more are in the planning stages. It is too early to say whether small modular reactors will become a significant part of the world's energy mix. The economics are still uncertain. The regulatory pathways are still being developed. But the idea is alive, and it represents a different vision of what nuclear power could be. Not a giant, one-of-a-kind project, but a standardized, repeatable product, more like an airplane or a ship than a cathedral. And then there is nuclear fusion. We have spoken throughout this long story about fission, the splitting of heavy atoms. Fusion is the opposite process, the combining of light atoms into heavier ones. It is the process that powers the sun and the stars. In a fusion reaction, hydrogen nuclei are pressed together with such force that they overcome their mutual repulsion and merge, forming helium and releasing a large amount of energy. The promise of fusion is very great. The fuel, isotopes of hydrogen, is abundant and widely available. The waste products are much less hazardous than the fission products from a conventional reactor. And the reaction is inherently safe in a way that fission is not. If something goes wrong in a fusion reactor, the reaction simply stops. There is no chain reaction to run away, no meltdown to fear. But fusion is also extremely difficult to achieve on Earth. It requires temperatures of millions of degrees, hotter than the center of the sun, to make the hydrogen nuclei move fast enough to fuse. Containing something that hot is an enormous engineering challenge. The two main approaches are magnetic confinement, where powerful magnetic fields hold the hot fuel in place, and inertial confinement, where lasers or other beams compress a small pellet of fuel. Both approaches have made significant progress over the decades. Experimental reactors have achieved fusion. They have produced more energy than was put into the fuel. But no fusion reactor has yet produced more energy overall than was consumed by the entire system, and no fusion reactor has yet operated continuously as a power plant would need to do. The path from experimental success to practical, commercial fusion power is still long, and the timeline for when or whether fusion will become a real source of electricity is genuinely uncertain. There is no confirmed date. There is no guarantee. There is only patient, steady research, much like the patient, steady research that led from Becquerel's plate to Fermi's pile. Fusion may become the energy source of the future, as its supporters have been saying for decades. Or it may remain just out of reach, a beautiful idea that never quite becomes practical. We do not know yet, and that not knowing is part of the honest record. As we come to the very end of our long walk, I want to gather up some of the images we have passed along the way, not the facts and the dates and the numbers, though those are part of the story. The images, the ones that stay with you when the details have faded. A photographic plate wrapped in black paper, tucked into a dark drawer in Paris, fogged by something invisible. A shed with a leaky roof, where Marie and Pierre Curie stirred boiling vats of pitchblende with iron rods, year after year, to isolate a glowing speck of radium. A walk in the snow in Sweden, where Lise Meitner and Otto Frisch worked out that the nucleus had split, that the atom had been broken open. A squash court under a football stadium in Chicago, where a pile of graphite blocks and uranium lumps sustained a chain reaction for the first time, while a calm man with a slide rule checked his numbers and then broke for lunch. A speech at the United Nations, where a president who had seen the destruction of war spoke of turning swords into plowshares. A small plant in Obninsk, sending its first modest current into the grid. A control room in Pennsylvania, where operators struggled to understand what their instruments were telling them, and a containment building that held. A great steel arch sliding slowly over a ruined reactor in Ukraine. A monument to an accident that should never have happened. A seawall in Japan, overwhelmed by a wave that no one had imagined, and workers who stayed at their posts in the dark. These images are not the whole story, but they are the shape of the story, the arc of it. From a mysterious glow in the dark to the quiet hum of a turbine spinning at 3,000 revolutions per minute. From an invisible particle to a lit house on a quiet street. And that is where I want to leave you, as you drift towards sleep. Picture a quiet control room, somewhere in the world, right now. It is late at night. The lights are dim. The operators sit at their panels, watching the screens, sipping coffee, logging data. The dials show steady readings. The chart recorders trace smooth lines. The reactor core, somewhere beneath them, is humming its silent hum, splitting atoms one by one by one. The steam is flowing through the pipes. The turbine is spinning. The generator is sending electrons out into the grid, through transformers and substations and power lines, to the lamp beside your bed, to the clock on your nightstand, to the quiet dark around you. The chain is unbroken, from the neutron to the nucleus, to the turbine to the light. The long arc of this story, from a curious physicist in 1896 to the room where you lie now, is complete. There are still questions. There is still uncertainty. The waste sits in its casks, waiting for a permanent home. The debate about safety and cost and necessity continues. New designs are being drawn, new possibilities explored. The story is not over. But for tonight, for this quiet moment, it is enough to rest in the knowledge of what has been built and what has been learned. The atom, which was once a mystery, is now a tool. The chain reaction, which was once a theory, is now a steady source of warmth and light. The quiet engine runs on, in control rooms and turbine halls around the world, a testament to the patience and care of the many hands that have built and tended it. It is not a perfect technology. It carries risk and it leaves a legacy. But it is ours, a human achievement, born of human curiosity and human effort and human fallibility. Let the images settle now, one by one, like leaves falling onto still water. The fogged plate, the snowy walk, the squash court, the first lights, the steel arch, the spinning turbine, the quiet control room in the small hours of the night, and then let them go. Let them drift away. You do not need to hold on to them. The story has been told. The night is still around you. The quiet engine hums, somewhere far away, and you are here, in the dark, breathing slowly, letting go. From a glowing photographic plate to a lit-up house. From the smallest things we know to the largest machines we have built. From curiosity to knowledge to power to responsibility. The arc is long, and you have walked its length tonight. Now it is time to rest. Close your eyes, if you have not already. Let your breathing slow. The story is done for now. The quiet is yours. Sleep well.